So I want to thank everyone for joining our second Open Source Science for Earth System Observatory Mission Data Processing Study workshop. I know that's a mouthful there. We have a large group of attendees. We have over 200 participants registered, so we're very excited for that. I know many of you may have joined our workshop number 1 that was kicked off in October of last year. Thank you to all who did participate in there. The report is available online. You can find that on our website address, and I have a slide on that later. But again, your time and your commitment to NASA's Open Science Data Initiative is very, very much appreciated. I did want to make a comment. If you are here, that means most likely you registered for attendance. But if you did not and you were somehow maybe forwarded a copy of the Zoom link, we ask that you take the time now to register. That registration link is also available on the website. We do this because we like to keep track of all of our attendees and make sure you get correspondence after the workshop and during the workshop if anything does happen to change. Let's see, did the slide advance? Yes, it did. Sorry, I have 4 monitors. I especially want to thank the Earth Science Information Partners Federation, ESIP. They're hosting this for us. We couldn't have done it without you. And you'll see them inside of the attendee list. And if you do happen to have any technical difficulties during the workshop this week, please feel free to contact staff at esipfed.org. This workshop is being recorded. As you can see, all proceedings will be publicly available on the workshop like they were last time. We do ask that you use your full name, your first name, and your last name in your display screen name. This way, it will help us identify you if you ask any questions or if you need any kind of technical support. Did the slide advance? There we are. So we do have several MCs over the course of this week. They are the study steering committee. So you have Sarah, Karen, Shell, Andy number 1, Luke, and Andy number 2. I'll take Andy number 2 for this workshop. So the speakers, you will receive a warning when you're at time or getting close to time. I believe Sarah will be letting you know of that. We do have designated question and answer period for our workshop. It's on the agenda. It's called Fishbowl Discussion. So please direct any questions or comments directly through the Zoom chat. But if it's a question that you want for the larger audience, we're using the Slido platform. If someone could actually put the Slido URL inside of the chat for everyone now so they can use that. And Slido is a very cool platform because it allows you to upvote depending on the popularity of the question. We will be prioritizing the questions coming from our SOG, which is the Systems Architecture Working Group first, but we will be answering all questions from all participants. If the time doesn't permit, we will make sure they're answered either in line via chat or afterwards. We do have scheduled breaks throughout the day, and at the end of the day, we do have breakout groups, which we'll have more on that topic later. So next you should be seeing the website. Here's the website link at the bottom. I think we'll be posting all of these links also. So if they're not available on the website yet, we'll put them into the chat. So again, if you know of anyone who wants to join, have them go to the website and register. So we do have a very full agenda for the week, and I want to thank all of our presenters and those also who responded to the RFI that was released. So the way we have separated our agenda this week, we have different sessions. So the first session of today will be the science collaboration approaches. And then later on this afternoon, we will be having one on NASA Earth Systematic Mission Processing Architectures. On Wednesday, we'll have the NASA Earth Science Pathfinder Mission Processing Architectures, as well as the non-NASA Earth Science Mission Processing Architectures. Thursday, we'll have the non-Earth science mission processing architectures continued, as well as the system interfaces and standards. And we wrap up on Friday with other big data processing system architectures. So we do have a code of conduct for our workshop. The main principle here is that all participants are treated with respect and consideration, valuing a diversity of views and opinions and thoughts. So in the event that, make sure I'm on the right side, that you feel any of these rules have been broken or being broken, please notify me. My email address is at the bottom, andrew.e.mitchell@nasa.gov, and I will be sure to address them immediately. I will now hand things over to Andy number 1 with the goals of the workshop.
Thank you, Andy, and good morning, everyone. Thanks for joining us today. I'm just going to give a little bit of context to this workshop and then pass it over to Kevin Murphy to continue the welcoming. So next slide, please, Andy. Andy, next slide. There we go. Okay, so many of you have probably heard of that NASA is developing the Earth System Observatory. You'll hear a lot about this over the course of the week. We use the term ESO. Core to that, this observatory are 4 missions: the AOS, Mass Change, SPG, and SDC. 4 missions that are currently under development at the moment. They're in pre-phase A. The idea here is that they're all going to be working together in tandem to create a full Earth system view of the Earth. As I said, they're in pre-phase A at the moment. They're preparing for mission concept reviews in this year, with the exception of SDC, which is going to be pushed out into the future. And that's because we have NISA that's under development at the moment and is due for launch, I believe, next year. So that'll be a pathfinder to the ESO missions. So we have these 4 working together, to create this holistic view. But the current approach that the missions are taking is the traditional approach of building their science data processing systems independently, working, within the concepts of within the scope of their particular missions. So Kevin Murphy, who's the Science Mission Director, Chief Science Data Officer, basically said to us last year, said, hey, we've got a window of opportunity here to reimagine how we do science data systems. Can we look for a more common approach to being able to have a more integrated view across these missions and the way we do this processing, and support the general NASA view of trying to create a more integrated observatory. So next slide, please. So Kevin basically set out the goal for us to identify and assess potential architectures that can meet the ESO mission science data processing objectives, promote the open science principles, and we'll hear a lot about that during this week. Search for data efficiencies across these missions. So can we collectively do things a little bit cheaper and more efficiently than we've done in the past, and also support this idea of an integrated Earth system science and Earth applications. So that's the study goal that we've been given to us by Kevin last year. Next slide. So I just want to quickly just sort of set some scenes here. So when we talk about the mission science data processing system, you'll hear the term MSDPS throughout this workshop as well. So what we're referring to here is the algorithms, the software, the compute infrastructure, the operational procedures, documentations that can automatically take these data you see on the left-hand side, push it through the system, and out pops science data products. And when we're talking about the scope of this system, we're also referring to the software tools that support the development of the algorithms and the validation and the analysis of the process data. So the architectures that we're going to be looking at over the course of this next week is really to look at that blue box that we're seeing in here, looking at what each missions currently do today and how we can potentially think of things in the future as well. Next slide, please. So to do this study, the steering team have put together, assembled an esteemed group, I should say, of architects that are part of this working group. And I want to actually just thank them all, take a moment to thank them all for contributing to this. They're all volunteering their time to support this activity. They're all experts in their fields, and they come from a diverse set of organizations and backgrounds, so we get a full viewpoint here into helping us build out these architectures. And I particularly want to thank Elias Safi from JPL and Natasha Stavros from the University of Colorado, who have been leading this working group and collaborating very closely with the steering team to help us put this workshop together. So again, thank you to all of them for the participation. And I know you've done a lot of work already, and there's going to be a lot more going on over the course of this year. So thanks for your commitment to this. Next slide. So the way we're approaching this study, as Andy sort of alluded to, we had first workshop in October where we basically heard inputs from the NASA program offices, and we heard from all the ESO mission scientists and data system developers on their requirements, and you know, looking for opportunities to improve things for the future. As Andy pointed out, the workshop is now available. The report is available on our website, along with a recording of the entire 2 days. So if you're interested in sitting down, you can absolutely do that. This workshop now, as we're moving into for the next 4 days, is to basically understand the current state of the mission and science data processing and obtain your input. So everybody here, we're looking for your input through the course of this week and beyond, right? So we'd love to hear from you, to hear what you're thinking about how we could be doing things into the future. Starting April or late March, the study team will then go away and start now doing their architecture study. They're going to be looking at different architectural options and essentially identify an optimal solution that can support these ESO missions. And with that, they'll be reporting our third workshop, which will be in August, which is a recommendation that we'll be making to Kevin. So again, in this March timeframe, this is the time we'll be collecting your input and your feedback on how you think we should be doing things. Okay, next slide. And I think this is the last slide. So this is what we're trying to do here today, well, the next 4 days. If we want to understand the current state of the mission processing systems, NASA, both in Earth, astrophysics, and also from other agencies. We're trying to look for opportunities for collaborating with other systems that we typically, mission processing system will typically interface with, so the archives and underlying compute infrastructures. So we're trying to look for opportunities for collaborations there. We also want to hear from big data processing systems that we can learn from them. And we did have a RFI, the request for information, that went out, and there we heard from industry partners that have ideas, and they'll be coming along on the last day to provide us some of their input. And again, I just want to emphasize, we're looking for your insights, we're looking for your recommendations, and we hope that we'll be able to get that. And so at the end of this workshop, there will be another report that will be delivered from Natasha and Elias and the rest of the team, and that will be made available. So with that, again, I thank you all. Have a great workshop, and I'm looking forward to this this week. Thank you. And I think the next, we'll pass it on to, are we going up to logistics now, or Kevin?
I think we're on for Sarah and Karen if they have any more logistics that we left out.
I don't have anything. I'll give people 2 minutes warning. That's all.
Yep, no, nothing. We can go ahead with Kevin. because I see him on. Oh no, that's Katie. No, wait, that's Kevin on Katie's screen. Sorry, that threw me off.
Kevin, off to you. I think you're on mute.
Can you see me? Can you hear me?
Yep, we can see you and hear you.
Okay, good. I can't see anything, but that's okay. So, yeah, thank you everybody for showing up today. We're back in headquarters actually today for a meeting with the Joint Program Planning Group with the European Space Agency. So, you know, one of the topics we're having here is open science and how that applies to our joint activities. So it's really you know great to be able to jump into this meeting just for a couple minutes and really kind of encourage everyone to look at what we're doing as we move into the Earth System Observatory timeframe. I'd like to give a lot of thanks to all the non-NASA participants and all the external participants. We're eating our own dog food here. We're trying to say, we're going to conduct open meetings. We're going to do open science. We're going to do this for the Earth System Observatory missions. So thank you for your participation. I want to say especially a bunch of thanks to the steering committee and to the SAWG members for their dedication and effort as we move forward in this era. So as you know, and probably have heard a number of times, the Science Mission Directorate developed a strategy for data management and computing back in 2019. And the basis for that was really looking at open science as transformational to all of NASA's Science and Mission Directorate activities. And Earth Science was designated as the lead implementing organization for that for all of SMB. And the work that you're doing here with this ESO processing study and workshops is critical to informing how we move forward and how we actually implement a lot of these activities for future missions. So really do appreciate your dedication, your support to this study and the development of the reports. But it doesn't end there. As we move into these open science frameworks and open science collaborations, your support and collaboration in those environments will be equally critical to realizing the capabilities that we are discussing through these ESO processing workshops. And our intention is to really enable greater access to the information, greater participation in the development of scientific and applied science and capabilities, all for us to make more informed decisions and to reach greater and greater audiences. So with that, I'm going to drop it over here, I guess, to Katie. Is that who's next? To give you a little bit more detail on these activities, but I just have to say, we've got a lot of really exciting things happening at headquarters that are going to be in support of ESO and in support of open science with ESO. Okay, next.
Hey all, you can hear me, right? And I'm going to try to share my screen out. So sometimes it doesn't quite work from here. I don't see a share button. Oh, I do. All right.
One second, Katie. You've been muted somehow. Try to unmute you. We can see your slides, but somehow you went on mute. Nope, still on mute. As soon as your slides went up, we couldn't hear you anymore. Oh, there you go. Well, there you go.
Oh, weird. Okay, I apologize. Sorry, technical difficulties. Apparently, it was trying to stream audio from the tab. So, all right, now you can see my slides. I'm Katie Baines. I am Kevin's deputy, Chief Science Data Officer, and I'm going to talk a little bit more, as he mentioned, on open source science. So Kevin touched on the SMD strategy for data management and computing for groundbreaking science in 2019 to 2024, which is a little bit of a mouthful. And if you really want to do your homework and read more about it, there's a QR code and a little bit.ly link there. But really, as he mentioned, it's about transformational open science. And there are three sort of main goals of that effort. I think you know, this activity here really falls squarely into goal 2 here, but I have some things, and we'll be starting to talk a little bit more about what we're doing with respect to goals 1 and 3 as well. So, you know, in more detail, you can look at all of the different elements of each goal. In fact, I will be talking more specifically about goal 1.1 in a few slides, but I just wanted to put this up here to sort of give you a flavor of all of the different sub-elements and objectives that came out of this this paper that was several years in the making. All right, so let's talk about open science versus open source science. So open science is sort of the practice, the collaborative culture enabled by technology. And we are really focusing on accelerating scientific research and understanding with open science goals. But when we talk about open source science here at NASA, it's really building on the concept of the open source software movement, which if you've worked with me before, you know is very near and dear to my heart. I'm really looking a lot more at earlier engagement in the scientific process and ensuring that all of the code that we do for our scientific processing is able to be reproducible. So it's really what we're doing at NASA specifically, we're calling open source science. So really, and as we talked about before, it's open source science is science, and I think you'll get a little bit more of this from Shell when she talks in a few minutes, but really leaning into the FAIR data, using more citations and data citations specifically. As I mentioned, increasing reproducibility, increasing collaborations, which is something we're working on right now here with our European counterparts. It increases citations and impact of the science we do. And we're also looking at sort of the other side of openness, which is really transparency and more equity and inclusion of new and historically underrepresented peoples and broadening participation in general. So to get into the details of what this means for the Earth System Observatory, here's sort of a template list of requirements that we at NASA are adopting for the science data products generated from this mission, this observatory. We're also working with our partners, so you'll see these bracketed terms partner throughout these sort of principles or requirements. And as we engage with various members of the international community on these new missions, we are ensuring that they are stepping up to the plate and also standing side by side with us in this open source science goals. Again, I'm not going to read through this whole thing. There's a lot more information that we'll be learning as we move forward through the pre-phase A and phase A processes. And I'm sure these will develop more color and detail as we go through. Now, the other thing I wanted to talk about, I think I'm going to make up some time here because it's going quicker than I'd expected, is the Scientific Information Policy, or SPD 41. And this is something, going back to this, these high-level goals, as I mentioned, is really about goal 1.1. Really the first thing that we were charged to do is really develop and implement a consistent open data and software policy tailored for the Science Mission Directorate at NASA. So this touches on not just the Earth science activities, but also our heliophysics, astrophysics, planetary and biological and physical sciences counterparts across the agency. So what we began doing, I think the person who's largely responsible for pulling this all together, Steve Crawford, props to Steve, and I started at headquarters on the same day. So August 2020, we sort of started down this road of developing it and building consensus internally. So let me give you a real succinct summary. Steve approved as open as possible and as closed as necessary. So we're preserving scientific information produced by NASA funding, which means that we are still, these are all numbered 1, which I just noticed is great. They're all number 1s. Preserving the scientific information produced by NASA SMD funding. This means that our archives are going to continue to be archives in the most meaningful sense of the word. So we're not planning on dropping any data or letting it all go, but we all also are looking to maximize the openness of our scientific information to the extent that our laws will allow. We're also, as I mentioned earlier, growing the community that can access this information and minimizing the burden of complying with that policy. So you can, as you can imagine, this is historically a large change. Although Earth Science has had a open data policy for many years now, probably decades. This is not, really the standard policy that has been in place for other elements of science data. So we are working to support that activity. If you want to look at the actual policy itself, that first QR code, which I hopefully now 2 years into the pandemic, we're all much more familiar with using QR codes, but that's a link to the actual PDF file. If you want to read more about the policy on the website, that link is also there, very similar but slightly different. And we actually are soliciting external community feedback, and yes, that means you. And we have had this RFI open for quite a while, but it is actually closing this week on the 4th. So this Friday is your last chance. So I encourage you to read through the policy, share your opinions and advice with us on it via the link, final link here. And there'll be another chance to QR code that later. So I'm sure inevitably this SPD brings to mind the definition of scientific information. Really, we're talking about publications, we're talking about software, we're talking about data. And when we talk about software, we're really talking about anything that provides scientific utility or produces a scientific result or service. It's not necessarily talking about small scripts that you're using to move files from one place to another, but if it's part of a larger activity that is quintessential to the data production lifecycle, that software would fall under this policy. So I think we've also talked about a little additional caveats or details about the policy. Publication, open access version as accepted manuscript must be accessible via NASA designated repository. We'll be working on the details of this as we go forward. That data shall be made publicly available without fee or restriction of use and no period of exclusive access. And the software should be released as open source software with a permissive license. Those of you who have been working or NASA funded in the past understand that this software release process has in the past been a little bit onerous. That is another thing that Steve Crawford has been working. He is our science data officer and has really been working at the headquarters and soon at the center level to ease that policy's adoption and application of the open source science policy and the technology release process within NASA. What does this apply to as far as timing? All future awards will be in compliance with this SPD 41, and this is being integrated in all the Roses 22 and Salmon solicitations. Roses 22, I believe the table of contents was released on Valentine's Day, so it's already out on the streets. And your PI should be cognizant of including these costs in the proposals responding to the solicitation. As far as current missions and grants, they are encouraged to adopt this policy to the extent possible within their current resources or as directed by their program officers. All right, so in addition to the main SPD 41 policy that is in place now, we are also doing an addition, SPD 41A, which really has to do with how the software is developed and a specific and explicit call out of fair and guiding principles, findable, accessible, interoperable, and reusable. This means that the software will, I'm just reading this. During the SMD reviews, peer-reviewed data and software shall be recognized as having commensurate value as peer-reviewed manuscripts. So this means that we're giving equal weight to code as we are to manuscripts, really trying to change the dynamic That means also that conferences, workshops, and symposium for which SMD is the primary sponsor shall be made information produced during that conference publicly accessible. So that means that this presentation that you're looking at right now already has a DOI and is already publicly available and uploaded on Zenodo. So I just also, another link to remind you that we want your feedback on this. And those comments are again due on March 4th. There's also an email if you don't feel like writing your question rises to the level of full-on response to the RFI. There is an email that has been set up specifically to field those questions. All right, so with that, I've sort of finished all my slides. I hope I am on time, and I think Shell will be going next. Is that right?
Yes. Thank you so much, Katie. Very informative. Appreciate you taking the time, you and Kevin, and how busy your schedules are. Now we will be turning it over to Shell, gentlemen.
Hi, thanks, Andy. Can you hear me?
Can hear you and see you.
All right, so we are kicking off the first session of the workshop, which is about scientific collaboration approaches. We really thought about the structure of this workshop a lot, and we thought it was really important to kick off all of this discussion about science data architecture and science data systems by starting with the people who were actually using the data, the expert scientists who are pushing the boundaries. And part of this new architecture is to support and enable new applications, new interdisciplinary science, just all new science, and to broaden who can easily access and build with the next decade of NASA data. So I'm really excited for our first speaker, Nayara Pinto. She works with the NASA ISRO Synthetic Aperture Radar NISAR mission during CalVal with ground partners who are interested in on-demand product generation. She also works with the UAV SAR, providing airborne data and in capacity building of SAR to a very broad user base internationally. She works with the NASA server program to build capacity internationally for working with SAR data and uses open science platforms as these resources are broadly available. So thank you, and here's Nayara.
Thank you, everyone. Good morning and good afternoon. Let's see if I can start my slides here. Let me know if you can see the screen.
We've got it. Thank you.
So my name is Nayara Pinto. Thank you for the invitation. I am the science coordinator for the UAV SAR instrument at JPL. UAV SAR is a test bed for the NISAR mission. And I'm also part of the Severe Applied Sciences team, which is part of the NASA Applied Sciences program. So one of the questions that I wanted to answer here is who are the customers and stakeholders? In my case, they are mainly researchers who work in environmental sciences who have some experience with remote sensing, but maybe not SAR. They're still learning about the best ways to use SAR. They're not experts. So I really need some involvement to make our processes not only reproducible, but easy so that these new collaborations can develop without a lot of upfront investment on their side. And hopefully these people will become early adopters of SAR, and we also get to do a lot of interesting science together. Some examples of collaborators include CAL FIRE, NOAA, and partners in tropical countries where I work on vegetation mapping. So this is one example here of one activity that we did in Gabon as following the AfriSAR campaign. And what we did was to try to show young researchers what the SAR signatures were in an area that was familiar to them, which was the city of Libreville. So our goals are to demonstrate our algorithms to non-experts, to enlist them to conduct accuracy assessment. And the requirements in this case are to integrate SAR with other observations. So we do multi-mission work as well as in situ observations. And some of the main constraints that we have are the availability of internet connection. So working in the cloud is becoming essential for us. What you see here is a picture of another activity that we did with young researchers, where there was a point where we said, okay, now it's time to download the DEM. And everything stopped, right? Because we didn't have any ability to download those large files. And that becomes a huge bottleneck when you leave the US. So integration with the GIS client and availability of Linux systems. So here is one example of a GIS client that we use, this QGIS. It's open source. A lot of people use ArcGIS, which is a proprietary. I'm not going to provide an exhaustive list of SAR applications, obviously, but I just want to provide a couple of examples to help get the discussion started. So this is one example of a workflow that we developed as part of the Servir project to map crops in Peru and Brazil. This is a very common workflow for land cover mapping, okay, where you have getting the imagery from the DAC. In this case, we're very grateful for on-demand processing by the Alaska Satellite Facility. We also get optical data from the LP DAC. And we work on Amazon, and we develop a training points using a Jupyter notebook. And these points are used, are pushed into a Google Cloud because this is where the platform is for expert interpretation. And that goes back into Amazon, where we run our model and make the crop probability maps available to the users. They can either download it using CloudFront, AWS, or they can just visualize it using a GIS client. What's interesting about this that I think that is a new open science application is the fact that this is a loop. It's not a one-way street, in that the user inputs can drive new iterations of the model. So once you have a probability map that can be evaluated by the end user, we can get inputs from them, which can be used to generate new training points to update this process until we reach an acceptable level of accuracy. And this can be used even for downscaling maps to specific regions. You can have something that works globally, but still needs to be refined at the more regional level. So this is a way to formalize the process and deal with this challenge of scale. What are some of the challenges that we've encountered here? Number one is, how do you transfer this to an end user who wants to take up the whole process, say the Ministry of Environment? And how do you make this deployable? How do you design this in a notebook first approach where the user doesn't have a ton of involvement with computing environments, which can be too much for that profile of user? They're not developers, right? So how can I package the environment in a way that's easy for them to reproduce? And then how do you integrate with the in situ data, including not just online platforms, but mobile apps, right? Where people can collect ground data that can be integrated with remote sensing data. And the last challenge that we have is some hurdles with cybersecurity. I work with our colleagues at cybersecurity at JPL, and I really enjoy working with them. What I've noticed is that we don't necessarily have a mapping of cybersecurity risk and open science users. And I don't think they have been sensitized about the need for procedures that enable open science, right? Where you're sharing the data is not only desired, but required. And so we don't have this risk category. They don't know where to put me. You know, why are you trying to do this? Why are you trying to open up your bucket so people can download your data? You know, so that's one example. Another example is an exercise that we're doing with UAV-SAR. We have something that's just getting started. It's called DenSAR. We're working with small notebooks for showing people, giving them small samples of data, right? And the UAV-SAR data processed in Pleiades, it goes to the NASA DAC at ASF. We download the data and to make it smaller and more manageable and do some simple processing like filtering. Then that's uploaded into the UAV-SAR website so it can be read by the user. In this case, we're using Google Collaboratory to do our analysis, which is a great resource if you don't have big volume of data, right? If you're just trying to do some small computations, the user doesn't have to install anything. It's a notebook first approach. So what you see here in blue is the code workflow, and that is working really well. We got our code base cleared, and the users can pull it using Git from Google Collaboratory. What's not working in my case, so I'm really interested in discussing options and hearing about other people's examples. What's really not working is the data path, right? In which I don't really have a way right now to work close to the DAC and to make those little data samples available without archiving them. How do you work with something that's not quite, you know, it's not going to Zenodo, it's not going to the DAC, it's just some small stack that I want to share with people for demonstration purposes, to just remove the learning barriers for these users who are really important collaborators. And we also need the ability to work with different cloud providers and perhaps have a more unified cloud neutral approach. Right now, I'm not allowed, I don't think, to share data in the Google Cloud. And that was the main reason for uploading the data into the UAV-SAR website. So that was a challenge that we encountered there. But this has been a really nice experience for us, and we've been able to share this internally, and hoping to share with end users from agencies like CAL FIRE, Forest Service, so they can understand visually for areas that they're familiar with, what kind of analysis can be done, in particular around fire scars. So what you see here is one example for the La Tuna fire, which was, I believe, the biggest fire in history for LA County, and it happened in 2017. This is what I had to present, and I'm just really interested in hearing your opinions on this. So thank you very much again for inviting me.
Thank you. We have enough time for a few questions. If anyone, I know I haven't seen anything on Slido, but if anybody wants to ask a few questions to Nayara, please feel free. Thank you for that great presentation.
Thank you. I'll put my email here in the chat box in case anybody wants to send me a message.
Shell, there's a hand up.
Okay.
For us.
Invite. I don't know how to
Thank
answer.
you.
There we go.
I'm good. Thank you. Thank you for that. Thanks, Shell. Thank you for the great presentation, Nayara. I was curious if you could clarify on the last point, the point you made towards the end about sharing your data that is not quite, or sharing anything that isn't quite sort of Zenodo ready. Can you explain what the scope of your need there is? Do you need to share it only, say, within users of your community, or do you need to make it available to the broader public in a more permanent fashion? Do you need them only to be able to download something, or do you need the recipients of what you share to be able, for example, to compute and interact with what you're providing? I'd like to understand a little bit better the scope so that maybe we can think about solutions. Thank you.
Thank you. We're interested in doing some simple computations. So just descriptive statistics, right? Do a histogram, do a transect, data exploration. They're not going to run an algorithm, a complex AI algorithm there. And that's why Google Collaboratory is good. Maybe Google Collaboratory can be used for complex things too, but I feel confident that it works. And ideally, I'd like for this to be open to the whole public.
Thank you.
Thank you.
Thank you. Yeah, I think that I hear more and more, Fernando and Nayara, about this sort of ephemeral small data shares that sort of fall between the gaps of the big agency repositories. So I think it's something that we do need to talk about more and get a better idea for exactly how we're going to enable that and what sort of scale the problem is. Or, do we need just 10 gigabytes? Do we need 100 gigabytes? How long do we need to store it for? Because I was just in another conversation with students yesterday about this exact issue. How long do we need to store it for reproducibility? What is the community accepted model? So
yeah, and
great.
if you want to see one example, the Alaska Satellite Facility has a page on data recipes. That's excellent. And the first thing they do is they say, these are the Python libraries you need, and this is the data, right? So how can we do it in a way that people don't have to do all this setup before they run the little recipe? That's the question.
That's great.
I would argue binder, but we can talk about the details later.
It's too slow. It's too slow.
Shel, can I ask? I want to ask a clarifying question to something Nayara said, because I understand that you're talking about sharing with these sort of small data sets, but you did also make a comment about governments that want to deploy whole workflows. And I know that with NISAR, that's, one of the things is that they don't have all of the higher level value added products that governments might want. So am I reading that correct? That it's not just small data sets. Sometimes the customers are bigger agencies that are interested in generating big products on big data.
Yes, so that was I have two examples. The first one was for big data. So we definitely needed to be scalable, and those governments are interested in using NISAR, for example, but the only thing that they have access to make things scalable is Google Earth Engine, whereas NISAR is in the Amazon cloud. I want to work in the Amazon cloud. I want the flexibility of working there, but I don't know how to make the whole workflow deployable so I can give it to the Ministry of Environment and say, hey, run this in your Amazon account. You're going to pay like $500 and you're going to get this for your whole country.
Okay, thank you. We have to move on and we'll have more time for discussion at the end, but thank you. So our next speaker is Willow Coleman. She is a senior at Harvey Mudd Claremont Colleges as a bioinformatics major and has been lead author on 2 manuscripts for urban ecology and produces value-added products from NASA, government, and commercial remote sensing assets using open science platforms spanning Jupyter Hub, Google Earth Engine, and others. So thank you, Willow.
Great, thank you. I will just share my screen. And can I get a confirmation that people can see my slides?
Yep, we can see and hear you.
Okay, great. So yeah, I'm Willow. I'll be talking today about imagining a new NASA computing platform with AI and big data supported analysis. So just a brief introduction. I'm a current senior. majoring in math and computational biology. I'm an incoming Schmidt Academy Fellow at Caltech. I have a wide range of research interests, including land cover and land use mapping, earth system science for environmental policy, and mainly integrating AI and deep learning into the field of remote sensing. So I'll sort of be talking about that a lot today. So to start off, I just wanted to talk about some of my previous experiences using NASA data with different cloud computing resources. First off, Google Earth Engine. So for those of you who don't know, Earth Engine is a cloud-based geospatial analysis platform that's specifically for visualizing and analyzing satellite imagery. So I've spent a lot of time working with Google Earth Engine, and I've sort of thought a lot about the pros and cons of working with this platform and how a NASA-specific computing platform could really be made better. So some pros are it has really clear documentation and like a vibrant online user community with a lot of support. There's an online GUI that's relatively intuitive to use and helpful for visualizing results. So just sort of making these figures on the fly for presentations. It can be linked with Google Colab, which is really useful for like GPU resources. And it also works with GitHub, which is important for version control. However, there are a lot of cons that I've come across, especially trying to use NASA data sets in Earth Engine. So the first thing is that a lot of NASA data sets aren't in the catalog. And I'll talk a little bit about that more later. So although some of them are there, if the NASA data set you want to work with isn't already in Google's catalog, it's pretty challenging to import local data sets and like work with them effectively. And a lot of that is because like there are computation and data storage limitations. So you're only allowed to like upload a certain amount of your own data. The other thing is that long-term free access isn't necessarily guaranteed by Google. It's free right now for any registered users, but that could change because Google is a private company. The other thing is that the main platform uses this sort of JavaScript-like code. And since Python is the main language for data science and has all of the open source libraries, it's sort of a limitation. The other thing that I've run into a lot is there are a lack of collaborative tools in Earth Engine. It's really hard to work with somebody else on Earth Engine code. So the next one is Colab. So Colab is sort of a Jupyter Notebook-like platform, but it allows access to a free GPU, which is really helpful for me as a student. I don't have a GPU, and so a free one is really great. And the fact that Colab has access to the Python libraries is really helpful for doing a lot of different data science and machine learning. The other thing is that it provides a consistent virtual environment between devices and can be linked to GitHub. So I've seen some papers that like have links to their Colab notebooks that allows me to just run their analysis right from my computer without having to set up a new virtual environment, without having to download any packages, which is really great. And I think that encourages a lot of important open science principles. The cons are pretty similar to the ones with Earth Engine. Long-term access not guaranteed. It's hard to import local data sets. You either need to import it into Earth Engine or import it into your Google Drive, which is slow. And if you don't have unlimited drive storage, that can also be a challenge. So I wanted to sort of go into a case study of working with eco-stress data. So that's the land surface data, land surface temperature data that I've worked with a lot. So when you go to the eco-stress website now for accessing the data, you have like at least 3 different ways that you can access their data. So there's the Earth data search, which is just downloading like raw H5 files. There's Appears, which is USGS's sort of like analysis tool that doesn't really require any coding, but you can get like little analysis points from that. And then there's just, accessing it straight from the NASA computer. So there's a lot of different potential ways to access the data. And that's sort of what I wanted to get into and why I think there's like a better way to imagine this. So right now, the way that I've processed eco-stress data is downloading 2 separate files for each tile to my computer. First, the geolocation data, and then second, a file for like LST evapotranspiration. Higher level products, you have to download a separate one to your local computer. Then I set up a Python environment, run this script that was provided by the eco-stress team, and it outputs a TIFF file that then I can use for my analysis. So there's downloading 2 files to create every 1 TIFF file. So there are some limitations to this current DAC system. From my perspective, the first thing is that NASA data is stored in multiple DACs, even for the same satellite. So you need to know which DAC stores the type of data that you want. It can be challenging to keep track of data sets if you're downloading from multiple DACs. Maybe you forgot that you needed to get a TIFF file from LPDAC and there's something else from like the Oak Ridge DAC. The other thing is that using NASA imagery data right now can require a certain level of coding ability, which is fine for me as like an undergraduate computer science major, but maybe not for everybody else. So sometimes the data is stored as TIFF files, which is great. There's like minimal processing necessary for science. And then sometimes it's stored as H5 files, which is useful for if you want to do like any sort of processing with the raw data, but then you need to geo-reference it to use it for science applications. So there's different end users require different types of data. And that, like I mentioned, this appears tool is easy to use and there's no coding required, but it can take 12 plus hours to run a single point file query. So it's really slow, and not all NASA data sets are in Appears. So I sort of had this broad idea of like reimagining it, NASA data access and processing in like a single unit. So there would be this sort of data lake that contains both raw and higher level products. So you can access it as like the raw data, but you could also access like already processed TIFFs for people who don't like have the computing ability or the need even to work with the raw data. And all of this is like easily importable into a web-based computing platform, sort of like Jupyter Notebook, but with that like GPU enabled. One, and it's sort of all in one place. There's no like searching for different types of data. So some sort of characteristics of this platform that I imagined is useful are first that it's collaborative. It would be really great if there's some way to like pair code, live code, share code easily between partners if you're working with somebody from far away. I've really enjoyed like in Visual Studio Code when you can live code with somebody else. So I think if there was any way to do that, that would be really important for enabling like collaborative science. And the second is open source code, definitely like supporting Python because that's the language of data science. Also the ability to like export final products locally. So maybe you want to do initial or further analysis outside of this computing platform, maybe run it in QGIS or ArcGIS. The ability to export these products and share them is really important. The other thing is discussion enabled. GitHub right now like has the ability to like talk about code. So if you're trying to encourage open science, having ways to discuss the code, obviously to like the extent possible with like data sharing practices, I think that that would be really useful. The other thing is GPU resources. Obviously there are like money concerns here, but as a student, having access to like a cloud-based GPU is really important to me. And the last thing is that it supports multiple user skill levels. And I'll also talk a little bit more about this, but building a platform that can be used by like more people than just research scientists and like academia is really important to me. So this idea of like broadening science participation, I was like asking the question of like, who are the end users for NASA data? First thing I thought of was researchers and government, academia, and industry. The most important one to me right now as a student is like education. I think working with NASA data has taught me a lot about things. And I think I wish that that was more available at the college and even before that level. The other one is community scientists and activists, people who maybe traditionally have been excluded from NASA science, but could really benefit from that data, and really like everybody else. So how can the next generation of NASA's data platform be more accessible? First one that came to mind for me is documentation and usability consistent with multiple levels of user experience. So starting off with beginners who have minimal coding experience, developing some sort of very simple like visual UI for them. They're going to be working with like those higher level products, just looking at the imagery maybe and some like building simple histograms and things like that. But this should also support advanced research scientists. So that should have those GPU resources available, the ability to develop more complex algorithms in this platform. It also should support Python for integration with data analysis packages, for AI, ML, and more. A lot of Python stuff is open source. And this also would build into a system that like incentivizes and encourages the development of more open source software. And building on this, like the emphasizing doing science that follows the FAIR principles that have already been mentioned today. So just in conclusion, I'm imagining some sort of platform that's a unified platform for both accessing and downloading NASA data, but also doing computing for data analysis, algorithm development, and more. And this would have a relatively simple UI and clear documentation to support user bases with different skill levels, would be open source, collaborative, and cloud-based. Thank you so much for inviting me to this talk, and let me know if you have any questions.
Thanks, Willow. This is great. I realized after our last talk that the minute we start talking, we're not going to want to stop, and we have discussions at the end. So I'm going to try to get us back on schedule. Please ask your questions in Slido so that we can go back to them at the end of this session in the discussion. And we're going to move to our next talk now. I also wanted to highlight that in Slido, we've just enabled reply. So Doug and George, Steve Crawford is aware of your questions. He is the expert on SPD 41 and SPD 41A, and he will be replying to your questions directly pretty quickly. I think he's at lunch right now. So thank you. Our next speaker, and please try to keep all your questions over on Slido, just so as organizers, we have one place to record everything. It just will make our lives a little bit easier. So our next talk is Morteza Karimzadeh, and he's a spatial data scientist with research and contributions that cut across geographic information retrieval and machine learning. He's the lead on this really exciting NSF project called Harmonized Earth, which is a collaborative research and capabilities development effort for creating algorithms, models, software systems, and cyber infrastructure for harmonizing big data products in a cloud environment for various downstream tasks, which when I read about this sounded a lot like what we're looking for here. So I'm really glad and excited that he was able to join us and talk today. So Morteza, please, thank you. I don't hear you. I see your slides, but I don't hear you. And he's just getting set up in a new house. So this is.
Can you hear me okay now?
Yes, now we can hear you.
Awesome.
Thank you.
Thank you. Yeah, sorry about the echo. It's an empty void here at the moment. Well, thank you for having me here. This has been a really exciting set of presentations. I think this talk, short talk, builds very nicely on the previous one. I'm assuming everyone here understands the values open science as well as open data, open source science and data, as well as open data and science, right? So what Chell and I talked about was to showcase a science use case, and I thought we'll all talk about the challenges of applying deep learning to Earth observations, and what are some of these challenges that can be tackled as a community and with shared resources. So that kind of underlies the tone of my talk for deep learning, for mapping, in our case, of sea ice. So we are very excited about our project that is kind of a year into it. There's a couple of years or 3 years left, funded and supported by an NSF EarthCube Award for harmonizing multiple data sets, for mapping sea ice. The idea is to kind of lift the barriers for geoscientists that are working with these kinds of data sets and making mapping tasks a little easier by providing user-friendly data management and machine learning-based pipelines, right? But you know, my statement is always, before there is open science, there has to be functional science. And with this generation of deep learning approaches for remote sensing, there are unique challenges that can also benefit from that open approach. So let's take a look at that. What we're looking at here is just a Sentinel-1 image acquired in the extra wide mode, and the corresponding sea ice charts, in this case produced by the Norwegian Ice Service. So these ice charts, or maps for that matter, are up to this date generated manually by Ice Service experts. So these are quite complicated. I have tried to sit in multiple labeling sessions or ice charting sessions to try to learn it myself, but I don't think I'll ever be qualified enough to create these ice charts myself. The existing algorithms for generating these maps are not that performant. Even deep learning struggles. The reasons are both the kinds of noise that are present in this data, as well as the ambiguity of the SAR returns over sea ice in the Arctic. There is a high ratio of noise to signal, or low signal to noise ratio, as well as ambiguity between different ice types and open water. This is even complicated more when you have meltwater during the melt season on top of ice. So the way we wanted to approach this, as a bunch of several teams around the globe, was using deep learning and convolutional neural nets. Really at the core of it is that they look at the spatial context, and therefore they have an advantage over existing methods, random forests and such, that look at handcrafted features. By handcrafted features, I'm talking about features such as NDVI. As good as they are, they don't really take into account all that much the spatial context. And we've had some progress. So far, we're only working with SAR data. So the idea is to go from this image to this higher resolution ice chart, right? Like I said, so far, this has only been done manually by ice experts at national ice centers around the world. And we trained models, and we, as a lot of other remote sensing experts here can attest to, we have generalization problems. So if we took the model and we applied it to an unseen image, we see an output that does not look quite like what it's supposed to look like, right? And what we see here are these bands that are essentially the noise that is left in the Sentinel-1 products. Even ice centers, for that matter, don't use Sentinel-1 imagery, or at least the extra wide mode in the work. They do use the IW mode because of this high noise. But this is the open source data set that is out there. ESA has invested a lot into launching the satellite, acquiring the images over the Arctic. But there is a little bit of gap between making these products analysis ready and denoising them. And we have used the best denoising algorithm that is out there out of our colleagues working in the Nansen Center in Europe, and still we see the noise effects on these images. Granted, with multi-source data, this is alleviated to some extent, but not a whole lot. Now, what I want to point to here, is less about algorithm and how good or bad it is, but how are we doing this? These images are large. We're talking 8500 by 8500 pixels. And the way remote sensing experts and most of us do this is to subdivide and divide these images into super pixels, or sub images for that matter, or chips as they are called, and then feed it into a deep learning algorithm, because otherwise it wouldn't fit into the memory, and we lose context in just doing that. We lose spatial context, which is kind of the strength of using deep learning and convolutional neural nets. So let's set that to the side. I want to revisit that. After we saw we were seeing a lot of noise, we said, okay, let's use deep learning and autoencoder again for improving our denoising over Sentinel-1 EW mode. And this is an image acquired over open water in the Arctic, right? So we shouldn't be seeing this scalloping horizontal lines here, as well as these vertical bands that we are seeing. This is just an artifact of the way the bursts are sent and images acquired in the extra wide mode by Sentinel-1. And the profile, as you see, this is supposed to be a flat line, but you see this this pattern of return. And this is the output of the denoise product out of the Nansen Center. So less noise, flatter line, but not that much better. And this is what really messed with our output, as I just showed you in the previous slide. So we applied an autoencoder or encoder-decoder network with skip connections. We optimized it, and we could alleviate the noise issue to a whole lot. In fact, you see a much better image with a much flatter horizontal, cross-sectional profile, right? And this is over open water, and I'm showing another image here acquired over sea ice. We see that our deep learning-based denoising, which works on top of the Nansen Center denoising, does help remove the banding and scalloping, as well as preserve the features. We've seen good contrast. The high-resolution features of ice are not lost. We need to do more experimentation here. But again, what is really the big catch here? We are only processing half, I guess, a quarter to a half of an image at a time, right? So For an automated pipeline, this can work in the meanwhile, but if we applied it to different parts of the image at the same time, at different times, we're going to see patches that don't necessarily continue in terms of brightness, and we need further adjustment to resolve that. But the reason I'm bringing all of this up is that we are running these on a decently potent desktop machine, right? And now we're deploying this on a computing cluster using GPU nodes to process the image all at once. But not everyone sitting here today should need to do that, right? What does it mean to lower the barriers, right? Not everyone can use Google Colab or Google Earth Engine for these kinds of use cases. Google Earth Engine, as far as I'm concerned, as far as I know, has really limited data sets available over the Arctic to begin with. So what are some of these challenges with these two simple tasks that I mentioned, right? So the overwhelming approach in the remote sensing community is to process images chip by chip. And subdivide into small pieces, then load them into memory because you need your mini batch to load into memory. The way we have made that denoising algorithm work is to load one image at a time into memory. And that's, I believe, 128 gigabytes of memory, which is a very expensive GPU. But what do we need as a community to not have everyone have a very expensive GPU to do that? Because even if you built that kind of model and that is able to process image all at once, but for the user to be able to denoise, then they still need a lot of memory to do the denoising using a deep network, right? And as a side effect of dividing into chips, we are losing spatial context, right? We are looking only at a small piece of the image in relative to the broader area. But more importantly, we are losing temporal context as well, right? In our case, sea ice is floating and moving and melting and freezing, and between each acquiring of an image by any sensor, things have changed, right? And the drift vectors give us a clue of where the ice is perhaps moving. So we could do alignment theoretically, not that that's any mature, that's a research frontier at this point. But remember, we are looking at images chip by chip. So we are losing temporal context. And temporal work is kind of the driver of all these improvements that we see in the land use, land cover, classification and mapping community. And we can't really take advantage of that at this point with the sea ice work, right? So that's why we're focusing on the multi-source harmonization of work. So really the case I'm making here in these 3 bullet points is that to do any of these things on the scale for which this is required, generating real-time products, we will need a high memory GPUs. And that is where I think there is a lot of opportunity for shared resources that are more accessible to the science community than just a single GPU, for instance, that Google Colab provides. Even their paid plans, the GPUs are not going to be able to handle this kind of work. Thus are resorting to supercomputers and clusters. The other case I wanted to make, I think, for deep learning, and I think this will be a tremendous contribution to our community, is pre-trained models, right? So deep networks are essentially a bunch of weights and biases that are optimized for a specific task. And the idea of semi-supervised learning is that, okay, we can have more generic tasks and we can optimize those weights for those tasks so that not everyone should do that again, but then maybe we can add a linear classifier or a shallow network on top of that and then only adjust that on top. So that's the big idea behind semi-supervised learning. And there are semi-supervised learning models, pre-trained models out there, ResNet with pre-trained weights, VGG, etc. The major problem is that these are trained on smaller cats and dogs kind of generic images, right? And we, at the same time, for any Earth observation kind of mapping task used in remote sensing, we don't have that much training data. So wouldn't it be nice for us to focus on generating more of these pre-trained models? So that we make them accessible, to generate that, we need a lot of memory. But once we do that, then the end user of that pre-trained model, the scientist, will not need that much memory. This is where I would love to see the Earth observation community to go a little more. There is a couple of pre-trained models on remote sensing data products, but not on that much. And lastly, harmonized products. We know about this. I could not hear you, sorry. Oh,
I think someone came off mute on accident, Morteza.
Okay, great. I just wanted to make sure I'm not past my time.
But you are past your time. Sorry.
I am past my time. So this is the last bullet point. The harmonized products that I think are missing. So we have Sentinel, we have Landsat and MODIS harmonized, but we don't have much beyond that. And multi-source data really deals with a lot of these issues that I brought up, noise, ambiguity. But again, doing that is something that is beyond the ability of an average scientist, someone like me, with the resources that we have. So these are some directions that I have identified. And I did want to mention that this is a lot of work that I put in a few slides, and our postdoc, Benjamin Lucas and Behzad Bahri, our PhD student, did the majority of this work, and I wanted to acknowledge the contribution of my co-PIs. But thank you for this opportunity, and I'm looking forward to the discussions.
Thank you so much for that great talk. Our next speaker is Qisheng Wu. He is a GIS, remote sensing, and environmental modeling, and is the lead developer on 2 incredibly popular libraries. He put a link to one in the chat already. These libraries focus on geospatial analysis and interactive mapping. There's GMAP, which works on the Google Earth Engine, and then he has ported that for a Python package that works in the Jupyter environment called LeafMap. These successful projects are widely used and have developed contributor communities. There's YouTube channels and tutorials, and just a really vibrant community constantly using these data sets and posting them. I think half the maps I see on Twitter are from these maps or these libraries. So thank you, Qisheng, and good luck with your talk.
Thank you, Ashel, for the very kind introduction. Sorry for my voice. I contracted a virus from my son that he brought back from the daycare. So, but luckily it's not COVID. I just tested this morning. So, but anyway, the talk of my the title is Cloud Computing Platforms for Big Geospatial Data, or Geospatial Big Data, whatever you may call it. And here is the outline. I will give a quick introduction to some of the popular cloud computing platforms for geospatial data. And then lastly, I will discuss some of my wish list for the mission data processing system. And so the first one is Google's engine. Some of the presenters already mentioned, and is, I think, the most popular cloud computing platform for geospatial data, launched in 2010. So it's more than a decade ago, but it only became public available in 2014. And one of the biggest advantages of Google's engine is the huge data catalog. So right now, has roughly 60 petabytes, so 60,000 terabytes of data. Of course, it includes a lot of NASA data. And so it has several major components besides the data catalog. So you can use that to do computation. It also provides the API, JavaScript API, Python API. It also allows you to create some interactive web app that you can allow users to visualize your data products. And so as you can see on the graph on the right here, the bibliometric analysis that I just did last week, and you can see the exponential growth of the publications using Google's engine, either in the title or in the abstract. So it's huge. I think this right now in the last year, over 800 publications. And so the paper that introducing Google's engine was published in 2017, and it has already 4,500 citations. So you can clearly see the impact it makes on the scientific community. But the downside is closed source, so it's not really open source. And it has JavaScript API that you can write the code, you can compute, and then you can visualize the data, you can interact with the data. It also has the Python API. So the Python API is relatively limited. You can think about Google's engine has 2 components, compute and visualization. So the Python only has the compute. excuse me, visualization is relatively limited. It's very difficult. So that's why I developed the GMap that makes it much easier. You can visualize the data, you can analyze the data, you can also interact with the data. So you can check out the website if you're interested in. I have a lot of tutorials. I also create the interactive web app that built on top of Google's engine and GMap that allow you to create, for example, satellite time lapse like this, using Landsat for the past 4 decades, and just within 60 seconds. So you can create time lapse any animation for any location around the globe using any Earth engine time series data. So you can not just for Landsat, Sentinel, Ghost dataset, whatever you want to use. You can try it out here, the link. So the next one, cloud computing platform for geospatial by Big Tech is a Microsoft planetary computer. So relatively new, launched in 2021. Kind of similar setup to Google's engine, but this one is just using Python API. So there's no JavaScript, but one nice thing is that it is open source. So it's fully open source. So you can, not fully open source, many of the components are open source. So compared to Google's engine, and it also utilized this spatial temporal XA catalog, meaning that you can use any data set that using the Stack API. So although right now the PC, the data catalog is relatively limited compared to Google's engine, but you can use anywhere as long as the data set is public available. So that's the good thing. It also supports scalar computing with task gateway. You can also deploy your own hub. And similar to Google's engine, I also create the leaf map package, not just for planetary computer, but you can definitely use that to, for example, source data interactively by ROI, by date, and you can directly load the data in the web interface. So this is within the Python Jupyter Notebook interface or Google Colab. That so in this way, we don't have to download any data. So you can retrieve the data from the cloud optimized GeoTIFF or Stat catalog, and then you can use that for computation, for visualization. And so the planetary computer actually brings a lot of ideas from the Pangeo cloud. And so Pangeo was launched in 2018, a project funded by NSF, and it is growing. It's a very vibrant community. So it's basically a software ecosystem that has so many software tools, for example, X-ray, DAS. So loads of packages have been widely used by the geospatial community for doing big data analysis. And of course, it's fully open. This one is fully open source, so you can use the ecosystem. You can deploy your own cloud computing environment. So planetary computer actually utilize a lot of Pangeo. Okay, and the next one is a Sentinel hub, and launched in 2018. So located in Europe, and is primarily used for basically making use of Sentinel, Landsat, and other satellite data. The downside is that it's not truly free. It has like different paid plans. They have the free trial, but it's quite limited. You can only view the data, download the raw data, and it's also closed source, not open source. Besides Sentinel Hub, so we also have the other one, OpenGeo. So this one was launched in 2017, funded by the European Commission. And the idea of this one is that we have so many cloud computing platforms. Right? Every platform has different API, and this one tries to create a unified API that you don't have to worry about learning Google's engine or Sentinel Hub. Basically, you just learn one, and then behind the scene you can switch the back end. But not everything is compatible, so it's actually quite difficult to do if you have different architecture. Although some of the common functionality you can implement. And the next one is Open Data Cube. So this one is from the Australian Sciences Data Cube and launched in 2017. The idea is that you have lots of satellite data and also utilize a lot of Python library, for example, also a PostgreSQL database that can manage the data. So it's also kind of a software ecosystem that you can use. You can also deploy in your own cloud computing environment. The last one is the MAP, so multi-mission algorithm and analysis platform by NASA and ESA. And so the version 1 was released in October 21. The initial focus area is just the biomass, and some of the data set includes every SAR and also JEDI and also the upcoming NASA mission. So those are some of the commonly used cloud computing platforms. Of course, everyone has their pros and cons. And so the lastly, this is kind of my wish list based on what I have learned from those cloud computing platforms. Although they are all dedicated to dealing with science lab data products and no raw instrument data, but I think we can learn from those data platforms. And the first one is reproducible. So anyone using the platform, if they publish the paper, they provide the code, other people should be able to reproduce. I think it's very important for reproducible resource. And the second one is replicable. That means if they develop an architecture or a system, other people can actually utilize what they have. They can deploy their own cloud environment using the technology they develop. The third one is sustainable. And this is one also very important because you're using something, you want it to be sustainable. But if you're using Google Sensing or Planet to Computer, okay, they are very good, but you don't know how long they're going to last because they are just from big tech companies for profit. Although it's free, but you don't know when it's going to stop working. And also interoperable. That means we have a very diverse data set, right? Lancet, MODIS, all kinds of data set. And these data sets need to be able to work together. Something similar to Google Sensing, like you can load any data set, they can just align together. And this makes it very easy to use. Also scalable, especially dealing with right now all the big global challenges. We need something that can be scalable. And also extensible, that means you have a platform, your architecture, other people can, because it's open source, you can build on top of what's already available, and they're just making better and better. The last one is ease of use, that you need to make it easier for other people, provide the API, simplify the stuff, but also provide the flexibility if other people want to do more complicated stuff. So those are kind of my some of the things that I'm thinking about, that if we have that kind of a mission data processing system dedicated to do raw data or raw instrument data, these things are also, I think, important, some of the characteristics of the system that we're providing. Okay, that's all I have. Thank you very much for your attention.
Thank you so much, Qisheng. That was a great talk. I really like the wish list at the end that we can use to guide the rest of our workshop, so thank you. Our next speaker I'm really honored to introduce is Dr. Fernando Perez. Dr. Perez created IPython while a graduate student in 2001 and co-founded its successor, Project Jupyter, which I'm sure many people here have used the Jupyter Hub, Jupyter Labs, and I can't really overstate the impact of Jupyter on not just scientific research across a huge range of fields, but also education and industry. It continues to make advances, all of the advances in development available to the world as an open platform that supports over 100 languages and is considered the universal science tool. It's vastly expanded access to science across the entire world. And he's working with NASA scientists doing research on ISAT and other NASA data. So thank you, Fernando.
Thank you, Shell, so much for that very kind introduction. Let me share my slides here. And for the opportunity to speak today, I will have a timer so we stay on schedule. So I will try to take a high-level perspective on Project Jupyter, which has already been mentioned by the previous speakers, and I'd be very happy to discuss further some of the issues that have been raised already. So you've already seen perhaps some examples of Jupyter notebooks in your everyday usage, and it's been mentioned already. Colab is effectively a proprietary fork of Jupyter from its early days. But the way I like to think about Jupyter is as a community, which is dedicated to building modular and platform agnostic tools for interactive computing, for the exploration of data, for the exploration of algorithms, for the understanding of problems, and for the entire process of scientific research around that. The Jupyter Notebook is one of the cornerstones, obviously, of the project. It's kind of the flagship application. For those of you who haven't seen it, it's a rich web client. I like to think of it as Google Docs with a brain, if you will. It's a web application with which you can construct documents. They can contain natural language, mathematics, formatted text, but they can also contain code and the output of said code in a single document. So they're effectively a narrative that combines a human narrative and a computational narrative into one. This idea, by the way, is not new to us. Jupyter did not invent this. Mathematica and Maple have had this well before we did, and there were open source implementations, but Jupyter's take on it, I think, is a little bit unique. Today, the modern interface around notebooks is a project called Jupyter Lab. It's part of the kind of Jupyter ecosystem. And Jupyter Lab is what I like to think of as a highly modular architecture for the kinds of workflows that arise in interactive data science. And so what Jupyter Lab offers is not only notebooks, they're still there. It's a web interface where you can still open your notebooks as before, but you can also have other tools. You can have actual, just regular command line terminals. You can have a console that executes code and displays, but doesn't build a document. In case you just want to run scripts and explore data without necessarily leaving a record, that console can actually be attached to the same notebook, that where you do have a permanent record, in a sense, giving you scratch space on the same memory and data and computational space as the notebook, but for things that you don't necessarily need to keep in the permanent record of the document as you're exploring things. The way perhaps I tend to keep a piece of scratch paper next to my notes where I test to see if a derivation is going to work. Data is a first-class citizen in Jupyter Lab. So just as much as you can open notebooks, you can open data and you can build custom data viewers. So for example, GeoJSON data can actually be visualized on top of a map rather than as raw JSON by itself. And the community can build their own. So this is an example of, over the span of 24 hours, a group of neuroscientists adding an interface within Jupyter Lab for visualizing neuroscience and neuroimaging data with a standard viewer that existed in the neuroscience community and was adapted for integration in Jupyter Lab. So this is why I say that it's a modular architecture and that exposes the components of Jupyter, notebooks, kernels, computation, data, within a UI and a set of JavaScript libraries or TypeScript libraries that can be expanded by the community. And these tools, in our mind, in Jupyter, are designed to really capture this kind of slightly cartoonish, but I don't think completely unrealistic view of the life cycle of research. We all perhaps try to explore some data where we have an idea in mind. At some point, we want to collaborate with our colleagues. Eventually, we need to run at larger scale. This point has already been brought up in the cloud on HPC. And then ultimately, hopefully, we have results that we can both communicate to our peers, publish, and if they become part of the canon of our discipline, we want to educate our students with these results. And what we try to do is think of this as a single connected set of ideas rather than a set of discrete steps where the arrow only moves one way, where you did your exploration in MATLAB and then you collaborate by emailing zip files, and then you rewrite your code in Fortran to get higher performance, and then you publish by copy pasting figures, and then you teach by making separate PowerPoints, right? Ideally, in Jupyter, there's components that apply to each of these that allow you to move both forward and backwards in that cycle, so that reproducibility and collaboration are kind of woven throughout the story. We don't have time to go into the details of all of these tools, but I'd be happy to discuss them further. I want to highlight a few points. Shell made some very kind comments that I deeply appreciate about our impact to give a bit of perspective. For example, when Katie Bauman, currently faculty at Caltech, presented her work leading the imaging pipeline of the Event Horizon Telescope, which achieved the first direct imaging of a black hole that humanity has made. She worked with folks at GitHub to draw the dependency tree effectively of which libraries and tools had gone into making their work possible, the work of her team possible. And it amounted to roughly 23,000 open source contributors that comprise a large community of creators that have fed into that. And one of the tools that was one of the key interfaces for them was Jupyter, as acknowledged in one of their papers. And we really appreciate the fact that such high profile scientific users actually take the time to appropriately cite and credit the core scientific libraries that they're using, which was great. more on an agency type project, the European Commission has a European center, which has a kind of complex acronym, the GEODPP. It's their big data analytics platform, which is developed as a Jupyter Lab interface on top of HPC and other resources that they have at the Joint Research Center, which is in northern Italy. And they have a very prolific Twitter feed where they provide kind of examples of the kinds of interfaces and analysis systems that they expose for the European science community. Pangeo has already been mentioned previously by Kui Sheng, and I believe Scott Henderson from the team is here in the audience. Hello, Scott. This is taken from his work. So the idea behind Pangeo is to bundle together Jupyter as the interface with other tools in the Python ecosystem, because Jupyter's role is the interactive computing part, not say large-scale distributed computing or data models and numerics. For those, other tools like Dask and Xarray are available, but they allow scientists to do this kind of thing. This is an example where Scott is zooming into a into an image, and after some little color bars wiggle at the bottom of the image sharpens. Big deal, right? You zoom into an image, the image gets sharper. We see that on our phones every day. Well, the beauty of this is that by Pangeo bundling all this in the cloud, the scientists can focus on zooming rather than on the color bars at the bottom, which is a cluster processing 100 gigs of Landsat imagery over the state of Washington, which would take a lot of engineering. And one of the previous speakers already made precisely this point when she mentioned that our domain scientists shouldn't have to become cloud engineers to do these kinds of things. They want to focus on their science. And this is what Pangeo is trying to enable. But I want to particularly highlight Pangeo because now I want to move into this idea of some of the lessons we've learned, that Pangeo has taken sort of a pattern of reuse, integrate, document, demonstrate, and contribute back upstream to the ecosystem that feeds you. And in this regard, it's a remarkable project that hasn't tried to sort of do capture, because capture happens in commercial settings, but also science projects sometimes try to be the only thing that people can use, but rather to work back with the ecosystem that feeds it in a sustainable manner. The existence of these tools in an open fashion also have an impact in education, as Shell mentioned. At UC Berkeley, our students can not only view textbooks online, but they can click on a button that takes them immediately to a hosted hub where they can run the computations on live notebooks. And this allows us to deploy the largest courses in data science on campus that serve thousands of students in a way that would be completely unthinkable if we didn't have these platforms. Anyone who's interested in the educational implications, I encourage you to attend the annual workshops on data science education that Berkeley runs. And so taking a step back from this modular model and these components, I think, and this kind of impact, I think it's worth asking, how does a project get to that point, since we're asking about how NASA can build platforms? And I think it's important to recognize that open source software is more than code. There's services and content that attract people. People don't necessarily come to your tools because of the code. They come because there's a paper they want to read, there's a result they want to share, there's an analysis they want to do. And so it's important for projects to think about kind of that tip of impact. The tools are also based on ideas. And in Jupyter, we've taken the time to actually document our implementation as protocols and standards that other languages can implement. And this is why today there's over 100 different kernels that work in Jupyter for different programming languages implemented by the community, because we've taken the time to not only provide an implementation, but an actual description of those protocols. We've formalized our community governance because at the end, it's people who maintain and create these ideas, and they need to be provided the right space, environment, and community for that to be possible. So it's not only the code that we have to worry about, it's this possibility of impact. It's how those standards and protocols build an ecosystem and how a community supports innovation and resiliency and the diversity of people, needs, and use cases that we need in science. All of these ideas are fundamentally variations on a theme, right? On the theme of openness, which I think is the theme of this amazing program led by NASA that I'm so excited to see, is that tools should be modular and composable. Let's please avoid monoliths. And as I said, monoliths can be private and commercial. They also exist in the scientific world where we build the one thing to rule them all and everyone has to come to our tool. I believe part of our success with Jupyter has been precisely that we provide the community with and the users with tools that they can compose to be empowered in their terms. Maybe they do need to run on a hosted environment. Maybe they need to run on their HPC facility. Maybe they want to run on their laptop. Maybe they don't need Jupyter Hub, but they need Jupyter Lab. Maybe they only want to think about the Hub as the one thing they log into it, and they don't worry about anything else. That ability, I think, is important. And I hope that these the future design discussion leads us to a path of this kind of composability of empowering users rather than asking them to come to the only one thing that we build. And fundamentally, that every project that is built in the future has a sense of contributing back to the open ecosystem that feeds it, because even scientific projects, I believe, have a responsibility to be good citizens of their ecosystems, if you will. So with that, I will stop, hopefully with reasonable time. I think I had 12 minutes, and thank you so much for the opportunity to speak today.
Thank you so much, Fernando. So now we're moving to a fishbowl discussion that's being led by the SOG. And I know that they have a whole series of questions for this discussion. Do you all want to come on camera?
Yeah, thank you, Shal. I can at least start a little bit here. What a great set of presentations to kick off this workshop. Wow, I'm amazed. Without further ado, we do have some questions that we're keeping track of. So I'll turn it over to our first question. Andrew Michaelis, please feel free. Andy, are you ready to ask your question?
Elias, I don't think they can unmute.
Okay.
So you may have to ask for them.
Since we only have 13 minutes, it might be good to just try and read them off and move it along.
Let me go ahead and ask those questions then, unless you can unmute those folks. So the first question is, and I'll just read it verbatim here, it's from one of our SOG members. There appears to be a theme of using multi-cloud strategy for data processing, end user data consumption, interaction / collaboration, feedback loops for models and new data products, etc. So how important do you think it is for NASA to consider a multi-cloud strategy for the ESO missions to better meet community desirements? Sort of an open question for a lot of the folks that may be involved in this, and maybe the speakers that presented here can take some priority. If one of you feel you can answer that question, feel free to jump in.
So since there's silence, I'll provide perhaps my 2 cents. I do think it's important for 2 reasons. One, I think, is avoiding vendor lock-in. I think it's very easy to inadvertently lock yourself into a single cloud vendor's ecosystem and effectively end up writing what becomes in practice proprietary code, even if it's open, but because it depends on that vendor's specific APIs. And so I think it's important to have workflows that give us that option. I think science should be sort of company independent. And second, because sometimes we also just need to use resources that are differentially available, right? It may be necessary for a given task to combine data sets that are hosted in separate cloud providers and that are impractical to move, or maybe there's unique hardware resources. And so I do think for both reasons, it's an important strategy to keep in mind.
Anyone else have thoughts on sort of the multi-cloud and how ESO missions can maybe utilize that to better meet their community needs? Or maybe even challenges. What's the challenges of using multi-cloud and going that route?
I do see a huge need to have cloud neutral implementations because different providers have different strengths and weaknesses. For example, we have a lot of good scalability in Google Earth Engine, but there's less flexibility. And we might want even to have some processes that are already done in Google Earth Engine and import them into AWS. It also adds a lot of resilience to our systems. in terms of being independent, like it was said here. I heard a lot from our stakeholders on that note. What happens if Google Earth Engine is taken away from us? What guarantees that it's going to be available? Do I want to build a whole monitoring platform on top of it, not knowing what's going to happen? So it's a risk to be dependent on to have that single point of failure, right?
Excellent point. Yeah.
Yeah, I can.
Any other? Oh, feel free.
Yeah. So for me, I think it's important to have different cloud providers. You don't want to, like as Fernando said, you don't want to be logged into one specific one. But for geospatial data, I think as long as you use some standard protocol, for example, Stack API or Cloud Optimized GeoTIFF, it doesn't really matter where the data are being hosted. But in terms of computation, I think it needs to be something. Keep in mind that if you have cloud providers, the user usually don't have to deal with individual cloud providers. So on top of that, you have a unified API that deal with different cloud providers. I think that would be something important for the users without having to worry too much about dealing with the data, but it's just using the same unified API, the same data access workflow.
Yeah, that definitely would be an excellent thing to have, but there's obviously challenges and ways to think about how to make something like that. Let me move on to sort of the next question. Hook, I don't know if you can unmute, but if you can't, I can go ahead and ask your question. Doesn't look like you can. Let me go ahead then. So here's a question from Hook, another one of our SOG members. Many diverse approaches were presented. Is there a general sense of what are the key and driving capabilities versus existing gaps across these computing platforms? So as an example, Qiuxing, you showed a useful wish list, right? What are the high priority items from that you would recommend for us to pay attention to? And keeping in mind, this is sort of the SOG and the steering committee trying to recommend an architecture for ESO missions. Also, Willow and Morteza, they mentioned some GPU limits and other things like that. So anyone want to take that one on?
Yeah, to me, I think open source is the top one. That it definitely, I mean, without open source, I can just use Google's engine. So why do we want to reinvent the wheel? But definitely it needs to be open source. The community can also contribute. That's my top, on the top of my wish list, that it needs to be reproducible and something that other people can contribute.
Maybe just even diving a little bit deeper, when you mention open source, right, there's obviously many, many different levels and many kinds of software. We're looking at the mission science processing systems, right, which is taking raw data and transforming it into some kind of usable science product. Obviously, the algorithms are, expected to be open source. There's processing systems, there's lots of scripts, lots of things. Do you feel the whole thing needs to be open source, or are there
probably
places
not.
that really are valuable?
As long as some of the key ones, for example, if you implement an architecture and somehow it needs to be some transparency, because NASA definitely is more trusted than other commercial big tech companies. And if we're using this system, we expect it to last for some time. But if you're using some commercial product, you never know when it's going to stop working. So I don't expect that the full entire system that it is going to be down. But if you're using something within the system, if somehow the system is down, is there any backup or any other way that we can somehow deploy this in other platform and then we can still get it up and running? Because we don't want to use a system that once it's gone and then all the efforts are wasted, right? Just like if you're using Jupyter, you use those packages, you know how to reproduce. Although we might not have the same computing capacity, but still we can somehow replicate what we run in the NASA computing system in some other low-level cloud computing providers, something like that.
Yep, thank you. I think you hit the nail on the head, right? They need to be able to reproduce and access and run those things, and that's the important part of that. Back to sort of that first part of the question, which I wanted to just repeat because I think we dove into the second part. there were many diverse approaches that were presented. Is there a general sense from where the existing systems are versus the gap to where they could be? And that sort of reference the wish list. So what's sort of that gap that you guys are seeing from the operational or existing systems versus what, the users might need, or what the next platform, in terms of a platform?
I could speak about that for a long time, because obviously in Jupyter we think about that a lot, but I would love to hear from folks like Willow, for example, who already did mention some of these points. What are her concerns? What are her constraints? Because this is a great opportunity to hear from folks who are both users and thinking about those platforms, so that we can get the feedback in the right way.
Yeah, I think, at least for me, the thing that is most important is having a space that everything is in one platform. I understand that other people might have, more unique uses that need specific platforms. Like, I liked your idea of showing that Jupyter thing of all the different parts of Jupyter and how they work together. I only ever use the Jupyter notebook. That's what I think of as like being most useful to me. So I think like being able to follow that sort of structure would be really important, because not everybody needs all these disparate pieces. And I think it can get overwhelming if you're having to pull data from a million different sources. Even if it's not actually that challenging, just starting to get towards that process can be a lot of effort. So I think having sort of that tiered system that supports multiple different user groups is really important. And that's sort of a gap that I see, because I have to go to different places to get like different types of platforms.
Yeah, that was definitely one of the things we wrote in our notes as far as access and having data either in a shared resource or at least accessible quickly. There was another question, and it was really inspired by you, Niara, but maybe others can, feel free to jump in, but I would like your perspective on this. You mentioned that it's a challenge to get access for end users to sort of the system that you're building. And this is a challenge that we're seeing not just in your system, but in a lot of these, especially the ones built by larger organizations such as JPL or others. So question for you, what strategies are you pursuing to get past those challenges? And more importantly, is there somebody else helping you across the project, or do you feel like you're the one pushing this to get it done?
I don't have a successful strategy yet. I'm still looking for it. There's two levels of collaboration. One is with the co-developers who are from universities outside of NASA. And I have a very hard time having them be part of my, just access a notebook and SSH into a system. That seems to be a big no-no. So on one hand, you hear, you need to collaborate, you need to make things open. On the other hand, there is a mechanics for doing this, right, within a NASA center. That's very hard. We have, I think, SPD 41, but we also have the Gatekeeper project directive that says, in order to access anything, you need to VPN from a NASA IP address. And then somebody else might say, well, you can't VPN unless you have a JPL laptop. So in order for me to collaborate with the university, I need to buy them a laptop, and they need a NASA badge. So the list of requirements becomes longer and longer, right? How much time do you have to actually do the science after that? And then the external users, we need clear directives from NASA that reconcile all those requirements, cybersecurity requirements with accessibility requirements. And I think it has to do with how much isolation do you need, right, from the NASA systems, such that the public can access data and code. Clearing the code has not been a challenge. We have a very nice streamlined process, but then allowing this code to run later by a someone, allowing someone to upload their own data into a server is a no-no. That's a huge gap. And then later on, sharing this whole system with someone is a challenge. I want to share it in a notebook first approach. I don't want to teach them how to build a notebook from the ground up because that's very hard. I wanted to be able to say, here's a notebook, you can attach some processing infrastructure to this and pay as you go, but just the notebook has everything you need to run this procedure, right? It has the environment, it has the libraries. So the main gap that I have is the cybersecurity and the notebook first approach.
Thank you for that perspective. There's no doubt. We do have some breakout sessions. So I think one of these questions here, just specifically this one, we will definitely explore and go into lower details into that. I know you have your hand raised up, Fernando, but I wanted to address Morteza here and see if he sees a different perspective coming from sort of a university view. Do you face the same challenges?
I think I'm gonna continue on along the same lines as I saw. Yes, we certainly do. For us, because we are in the training and education business, and there is some sort of limited time essentially for graduate student and postdoc, and this logistical setups from permission to low-level APIs to high-level APIs. I do think there is significant barrier along the same lines that Nayara just mentioned. So we do experience that a lot when collaborating, even sometimes within our own units. For instance, we work with the National Center, Snow and Ice Data Center, which is a NASA DAC here on campus. And to circle back to the previous question, I still do think there is like a little bit of gap between what we call as high performance computing and what deep learning needs as high performance computing. The high performance computing is being very heavily focused on CPU support and parallelization on CPU, whereas for deep learning, it's at the end of the day GPU. Speaking of multi-cloud, in this era, unfortunately, it's only mostly NVIDIA. AMD is becoming a player, but not all that much. The drivers are half open source, half closed source. You've been working with TensorFlow. There's only so much of the source code you see, then the rest you don't see. So by just stepping into this deep learning space, we are kind of signing up, unfortunately, for doing open science on top of closed code. And that I see as a long-term long-term threat to replicability. If we lose access to that lower level, whatever we have done open on top is going to kind of melt away.
Yep. No, excellent point there. I'm sorry to cut you off a little bit short, but we are due for a break here. I know you do have your hand, Fernando, but maybe we can come back to that one at our next fishbowl discussion. So I would recommend we start our break time. Thanks, folks.
Thanks so much to all of our speakers.
Thanks, everyone. We're going to take a 10-minute break, and we'll try to convene back with session number 2 at around 10 minutes, 7 to 10 minutes. Welcome back. That was a great session, session number 1 to kick off a workshop. We'll move right into session number 2. So the next session focuses on presentations from NASA's Earth Systematic Missions Program. So this program is a follow-on to NASA's early EOS missions with the objective of continuing to advance our understanding of the climate system and climate change. So our first speaker is Robert Wolf from NASA's Goddard Space Flight Center. Robert is the manager of Goddard's Terrestrial Information Systems Lab, as well as the Deputy Terra Project Scientist. So I'd like to welcome Robert Wolf. Can you hear me?
Yes, Andy, can you hear me?
I can hear you and I can see you.
Great. Okay. So let me see if I get my slides up now. Okay. There's this slideshow. So can you see my slides?
Not yet. Still see you.
Okay. So there's something here I have to do first. Probably.
Roberts, I have your slides up if you need me to show for you.
I think I can do this.
Okay.
How about now? Can you see my slides?
You're starting to share screen. Great.
There you go. Perfect.
Okay, great. Okay, now I'll see if I can change them. So anyway, thanks, Andy. This has been a really interesting workshop so far, and I've enjoyed hearing a lot of the applications folks talk earlier about open source. So anyway, so I'm going to talk about the Terra data system, and that was developed for MODIS. MODIS is one of the 5 instruments flying on the Terra platform. It's actually been up there now for 22 years. And there's actually 2 MODI. The second one's on the Aqua platform, which was launched in 2002. And the data system I'm going to be talking about is used to process both Terra and Aqua data, but I'm going to focus mostly on Terra for now. It's a science investigator-led data system. I don't think this term was around when we first started in 1999, but this has become what the systems are called nowadays. And the system itself is called MODAPS, the MODIS Adaptive Processing System. So it was developed before launch of Terra back in 1998-99. And it was originally the backup system. So there was a primary system, and for various reasons, they needed to go to the backup systems, which we had developed. And it had been developed by the science team for testing and getting ready for launch. And then we were actually able to smoothly fit into the whole ecosystem needed to process the data. It produces it originally just produced land, ocean, and atmosphere products, or just a large number of products for these various disciplines that we produce. Later, the ocean group split off, and then we inherited the level 1 products from the Goddard disk. And then since that time, we've evolved the system to process MODIS on Aqua, the VIIRS instrument data on SUMMPP, and JPSS, we're calling NOAA 20 now, and then soon there'll be JPSS 2 this fall. So the system has been able to process a lot of data and some other instruments as well. It's co-located with the LAD stack here at Goddard Space Flight Center, and it uses the same infrastructure, particularly the hardware infrastructure and many of the same software infrastructure. And we have an instance of it that we use to produce our near real-time product through the Lance system. So just to give you an idea of the scale, 1 year of MODIS, level 1, 0, all the way up through our level 3 products is around 180 terabytes per year. And so that's about, over the last 22 years, that's about 4 petabytes of data that we're constantly processing and reprocessing. So, so just to give you some background, some of you may not be familiar with some of these terms, so I wanted to talk about them a little bit. The first term is the ESDT, or Science Data Type, which is basically just an acronym that we give to each data set that we produce. And it's very important that we identify our data sets, and it allows us to generate these large number of different data sets. The other thing we talk about is our product generation executive. This is something, I don't know where this term came from, but it's essentially an application or process that actually generates the products. And these PGEs read one of an input data set and produce an output data set. And one of the things that when we talk about open science, we've been doing, I think we've been doing open science since well, I'm sure well before Terra, but in terms of the Terra modus, we've been publishing these PGEs, the source code for the processing since launch, and every version of the science products we produce. We also release the version of the science code that produces those products. And both the software and the data have been publicly available since early in the 2000s. And we look at each algorithm family, and it has a collection of earth science data types and PGEs. So if you kind of look on the right, there's a summary of, the number of PGEs just to do MODIS level 1 land and atmosphere products is around 131. And if we look at the product levels from, calibrated radiances at level 1 all the way up through model informed products at level 4, there's 131 products total. So, so in terms of other concepts, we have collection versions. So when we produce a new version of the product, we do a reprocessing. We also assign that a version, and that's the thing that we use, like we're on currently on collection 6.1, which is the 7th reprocessing. We also have archive sets, which are a set of related data from production or test data sets. And so each collection version is stored in a different archive set. And this allows us to keep the data, multiple tests and make distinctive, allow our science users in particular to come in and look at and say, comparing the output from one archive data set to another archive data set. And so when we're performing all of our testing, just a large number of tests that are needed to get to the next point in terms of improved quality, we use these archive sets to keep track of what's going on. So the other thing we do is we have a set of production rules for each of the PGEs. And these are very precisely specify what inputs are needed, what ancillary data is needed, if alternative inputs are needed, what we would do, and so on. And these may be different rules depending upon whether we do near real-time products for the particular PGE, or we're doing a reprocessing. They may be different production rules, but we have these really, it's one of the things that's really key to what we do. So if we look at the next slide, which is the MODAPS Adaptive Processing System, MODAPS, MODIS Adaptive Processing. It basically we build with commodity hardware. We kind of switched over from big iron to commodities in the early 2000s because it's easier to scale. There's lots of cost savings, and it's easier to do technology refresh. And so, and if you kind of look at where the cloud computing has gone, that's in some ways similar to what the cloud computing community grew up from some of these early days of commodity hardware. So we do build with open source components. We're almost all open source now. Linux, Perl, Postgres, Ceph for our object store. We designed the system to run pretty much standalone, so you can just turn it on. The pipeline runs overnight, over the weekends. Do large reprocessings where you don't need very much manual intervention. But we have tools, lots of tools for investigating issues with failed jobs and various other things, errors that you've encountered that you've never encountered before, because this is satellite data and that's the way things work. And we have a way of rapidly provisioning our servers and operating systems and libraries. So if you look at the overall architecture, it's a bunch of compute servers with archive servers. We use object stores primarily now for most of our data. We have a couple big switches that keep all these things connected. We have head nodes where the actual instances of our processing run, as well as database servers. Assume I'm not talking to a wall, but so if you look at the software architecture, we have a number of main components. One of the things is the operator dashboard, which controls the entire processing system. We have ingest, a scheduler that manages all the different tasks that are running, a loader, export manager, an archiver. But the real most of the data flows is between the object store and the compute nodes. And then you have data flows from the ingest and then also out to the community. And the rest of the smaller blue lines are the just control and sort of smaller data flows. And this is all, you know, the whole system runs within a production database that kind of keeps track of everything that's going on in all of these jobs and so on. We do have multiple instances. We have like a forward instance, a reprocessing instance, various test instances, and then we have 2 instances for our Lance near real-time systems, one that's redundant with the other. So what we're doing is we're generally improving the system over time, and we just have been continually improving the system. We have the adaptive processing system, which we're designing right now to be more general, and we're evolving into that. Part of what we've done already is the object stores, and we're moving into more of a continuous integration deployment mode. Most of our software now is in GitLab for these systems, and that's making collaboration with our science team members easier. And we're transitioning the services and processing now to Kubernetes and Docker containers. So it's very easily to scale out into the cloud or even run the entire system in the cloud. Finally, we're developing what we're calling Origin, which is captures the metadata and helps make it easier to do reproducible products. So the last few slides I have, I hope I have time, is just key lessons learned. First of all, you know, good collaboration with the science team is really important in making the systems run. It's all about the people. We do have a centralized QA group, which really helps us understand the products and uses tools and various techniques to really quickly turn around, you know, is this version of the product better than the last version, and help the science team understand the quality of the products. And validation, of course, is very important to our overall mission of getting these high quality data products out. Other lessons, you really have to be able to scale. Either, you know, these systems have to be able to go from, you know, 2x to 10x to we're probably at about 60 or 70 times real time right now, and use Moore's law to your advantage. Again, run on commodity hardware, do good pre-launch testing. You need to be able to do reconciliation because data flows are never perfect. You know, just fixing those leaky pipes actually can be quite a bit of effort in any data system where you have multiple different connected bits and pieces. And it's really good to develop algorithms that can run across multiple sensors. In terms of reprocessing, again, you have to be able to scale to be able to do that. You should have a separate test string where you can do, you know, multiple tests simultaneously and lots of data processing. And you just ought to be aware that over time you're going to be moving to different systems. We've moved from several different hardware architectures and software architectures over the last 20 years, and we expect to continue to do so in the future. So that's all I had. I hope I didn't run out of time.
Nope, perfect. You were right on time, Robert.
Good.
We actually have time for a question or two before we switch.
Anyone have anything? Are we going to have a question session at the end, Andy?
Yes, similar to the last session, we will have a dedicated session, another fishbowl session where we can have a follow-on.
Okay, so I don't see any questions in the Slido.
The
Slido.
Oh. So there are our study team has their own Slido, so they have a list of questions queued up ready for the fishbowl, so we can wait for those. So we
Okay.
can move to our next speaker. So our next speaker is Chris Curry from NASA's Langley Research Center. Chris is the data management team lead for NASA's Clario mission. Chris, are you able to?
Yep, just 1 second. Hang on.
Perfect.
Let's see. Hopefully I get this right.
I believe so. So you're sharing your screen, and I can hear you. And there's your slide.
You can hear me and you can see this? Well, that's great. Okay, my name is Chris Curry, and today I'm going to talk about, give you the perspective of Clario, some views, lessons learned on science data processing. So first, Clario has two main science objectives. One is to put in orbit the most accurate reflected solar instrument to date for operations. And the second on the right, which is what I'm focused on, is demonstrating the ability to do intercalibration in space. And so we will tie the reflected solar measurements from Clario Pathfinder to Ceres and VIRS instruments. We haven't launched yet, so we're not in production. We're still in development mode. So that's what I'm going to cover today, is what we've done to date and where we're planning on going. And so we launched December 2023. Okay, so this is a typical ground system. Our partners at LASP generated this, Tim Holden, back in 2020. So some of it's not 100% correct, but that's okay. On the left side, you have our instrument, the Clario Pathfinder, is mounted to the International Space Station. So the data goes down through existing infrastructures. It ends up at LASP in Boulder, Colorado, where they do the level 0 and level 1 processing. Then they transmit that data to at Langley to the Atmospheric Sciences Data Center. And so today, what I'm really going to be talking about is just this little blue box on the right, the Intercalibration Science Data System. And that's responsible for, as I said, intercalibrating the Ceres data that we pull in from the Atmospheric Sciences Data Center, and VIRS data, which we pull in from the LADS facility at Goddard. So this is, it's a typical, what a project has to do is you generate data flow diagrams for your science codes that you execute in production, and then you show your dependent input files that you need in the products you're producing. So I won't go through this in detail, but these are documented in the Clario Pathfinder ATBDs. But on the left shows the Ceres pipeline. So this is what we have to automate. And so when we receive the data from Clario Pathfinder, that kicks off this processing. We pull in the matching Ceres level 2 products. We spatially match the Clario Pathfinder data with the Ceres data by using the Ceres footprint, the Ceres point spread function algorithm, and that does a spatial convolution. Then we adjust the spectra. Oh yeah, I should say that the reflected solar instrument, Clario Pathfinder, is a spectrometer from 350 to 2300 nanometers. So there's like 640 wavelengths of information. So we're dealing with spectra data. What we need to do is match that, make corrections for the minor angular differences. I didn't show that. Let me go back to this. I'm sorry. On the right, this is an important slide. I should have gone through it. It shows the Clario Pathfinder is mounted to the International Space Station, which flies under the JPSS instruments, this JPSS satellite. And the VIRS and Ceres instruments are mounted to that. So one of the unique features about Clario is the ability, it has a 2-axis gimbal. So what we're trying to show in this image is co-aligned measurements. So the Clario Pathfinder predicts when it's going to fly under the JPSS satellite. Then it points to match the scanner's instruments. And so These events, this is one of the challenges, you know, is basically predicting when these events are, commanding the instrument to point, and we allow for up to 10 minutes of difference in timing, so that they don't have to be, you know, exactly pointing. They can be within 10 minutes of each other. Hopefully that made sense. So these are the codes for both the series and VIIRs that we run. One of the things that's unique about intercalibration, so it's different than other data systems. This is our current development system. So what we do is we define a plan, what we call an intercalibration plan. So we know we define the target and reference instruments. Clario Pathfinder is the reference instrument. We do something similar to what I just showed you, what the spacecraft command and control does is we use some orbit propagation code, 2-line elements from Celestrac, and we do event prediction. So we calculate when the instruments are observing the same real estate. And so we match in time and view geometry. Then what we do differently than most data systems is we query remote sites. So we go to the LADS OpenDAP server and you know, we find out the data that's available that we need, and then we retrieve that data, we bring it back, and then we actually process it. And so currently to date, since we don't have the Clario Pathfinder data, we have to do some complex radiative transfer calculations to simulate the level 1 data, and then we perform our 2 main pipelines, or the intercalibration algorithms. So we do retrospective analysis right now. We're not set up for forward processing. So this is a system, and I'll give kudos to the Access. You know, we started back in 2011, and we were able to get some funding to really develop this system, which is what I refer to as a hybrid development system. And so it's a web-based distributed tiered system that basically has really served us very well to develop and validate our codes. And so what this work, you know, we basically, as I said, we define an intercalibration plan. We run some prediction code. We talk on the right side to some external OpenDAP servers to pull in just the data we need. So we don't go through a typical ingest process where we like transfer all the MODIS data. We just go out and pull in the level 1 and level 2 data files that we need. And then the other thing that we've developed with this system is, if you go down to the middle bottom, our workflow, we use and I'll explain this more, but we use a package called Nextflow. It's an open source package for our science to execute the pipelines. And what's nice about that system is that it allows us, our traditional data systems at Langley have all been large clusters, in-house clusters with large shared file systems. And we've used Sun Grid Engine and Univer Grid Engine software to do our batch processing. So that's what we started with. We have a small cluster where we do our science processing on that system, but we've since expanded to AWS batch. So that's really what the focus of my talk is how we're transitioning this system, the pieces that we've learned to move to the cloud, what makes sense and how to best transition to the cloud. So that's what we're working on now. And this is sort of it just shows you, this is really, when we did this simulation, this was the first time that we actually ran a pipeline in the cloud. And it really showed to us and the science team the power of the cloud. Because radiative transfer, if you look over on the right, this is a pipeline, and a pipeline is basically, it's a bunch of processes. These blue little rectangles are individual processes that are part of this pipeline. And then the little ellipses are what's called in this Nextflow scripting language, it's channels. It basically is a set of software and that gets the right input files to the processes that you need to. But getting back to the point, this was the first time that these radiative transfer codes take a long time to process. And so we're simulating, we've got a little 0.5 kilometer pixels, but we're doing radiative transfer for scans of data. And so to simulate, just like several minutes of our data can take an awful lot of CPU hours to process. And so what we did in the cloud when we did this simulation, we would do in a few days what it would take us months of processing to do on our in-house clusters. So this was when we really learned, once we did this simulation, was really when we learned the power of AWS. So the other thing that we learned during this thing is they have a feature called spot pricing, where you basically can bid on, we would say we're just going to pay 40% of the on-demand costs. So that I would recommend that. But the downside of that is that, especially during the week, it's great for weekends, but during the week, somebody else can outbid you, and your EC2 node, your jobs running on that node will be, they'll fail. And so your soft, one of the nice things about this pipeline, this Nextflow workflow engine, is that it has the ability to detect failures like that and then resubmit the job. So we would, just to simulate a month of data is like 10,000 jobs to keep track of. And we were able to even though we had like 600 failed jobs, resubmit them and execute them correctly. So this was when this was a few years back, we first did this and learned the power of AWS. So to give you more, this is just another simulation study, but the only reason I show this is just to give you an idea, if it hasn't been clear, that these are events, what we call events, and they vary in duration from like 2 to 10 minutes is typically. This is 100 events that occurred during January of we're simulating this, of course. But you get about 100 events, intercalibration events, where the Clario Pathfinder instrument observations are matched with the target instrument series of years. And so we've been able to simulate with this tool on the cloud, simulate our algorithms for a year of data. But this just shows you what our data set looks like. So it's not covering the whole globe. So that's another reason why we just want to go out and figure out what the target data is at these remote sites and pull that in for the science processing. So I want to recommend some, this one's an obvious technology that we recommend, Docker containers. It's amazing what it can do. Once you get it working on your laptop, you get your code and the dependencies of the code, you're able to run that same code by just transmitting the Docker image to a different repository, either on your local cluster or on AWS cloud with absolutely no modification. So this is one technology you definitely want to master. The other, I would recommend Nextflow as a workflow engine. It's a DSL that implements data-driven pipelines. There's the URL. It's open source. It has one of the things that's nice is it's got an active user base, and it's from a bioinformatics community, but we've used it, and there's different executors. So like we came from working in a batch grid engine environment, and we wanted to go to AWS, so they had an executor to abstract that. Once you got your pipeline defined, it works really nice. Making that possible. There's other executors, so there's other cloud technologies that they support, but we're basically transitioning to AWS. The other thing I've mentioned that I really like is the pipeline report. Some of our pipelines have lots of, especially when we're doing reprocessing or doing our simulations, there's thousands of jobs to keep track of. And Nextflow does a really good job of keeping track of the resource utilization. And if there's a problem, pointing you to the right working directory so that you can fix your code and then resume that long execution. You do not have to redo the whole pipeline. The other technology that, and I guess another thing to mention is, I'm not an expert on these technologies, but if you did want follow-on information, the analyst on our team is really good at Elasticsearch and Nextflow. So he would give a better presentation. I'm just giving a high-level overview. But we use the Elasticsearch. It's a NoSQL database. We build a collection, our own data collection catalog that identifies the data that we need to retrieve, where it's located, where it's cached, and then when we generate a level 4 product, we keep that information. the Elasticsearch includes some analytics capabilities, so it allows us to find things quickly by space or time coverage. We can do some histogram analysis to identify when we think we're missing some input files. And one of the new features that we've just recently tested with our level 4 data is to add G-ring metadata. I think this is a standard that the EOS community recommended years ago, but we're using it to do put it on some of our products that we can then match more easily, go into our database and identify these small events that maybe match other data sets that are out there for studies. It's flexible, and we're impressed with the performance. All right, quickly, so now where are we at? Clario is, we're moving away from in-house clusters. And so for any project, there's really 2 types of data systems. You've got a production system, which is what the data management team is primarily works on, is responsible for. But you also have a science development team, what we call a science development team cluster, which are validation and algorithm development. So that's typically the projects I've worked with. We've kind of kept those resources separate, but they're basically large clusters with large shared file systems. So we're transitioning all of this to the cloud. And so this is the SDT cluster. It basically consists of this is the architecture that we've come up with. It's just one head node. So that head node you're paying for, it's running all the time. As you SSH into that, we have installed Jupyter Hub, and so we're able to, it runs Jupyter Lab and Jupyter Notebooks. We're really impressed with that for interactive analysis. And so that's one of the challenges. Did someone have a question?
You need to wrap up. We're at time.
Okay, quick. Okay, well, that's the one system here's our production system. So what we're transitioning to is a serverless architecture. And so I mentioned before, we weren't doing forward processing. So what'll happen right now is when a level 1 file comes in to an S3 bucket, it's going to kick off Lambda functions and step functions. We're communicating with our Elasticsearch database. So it's some of the same technology, but this is the recommended way to go. And the last thing, this is a slide generated by the Clario project scientists. Clario Pathfinders thinks, we're willing to support this open source science. There are abundant opportunities with the data that we're producing. 90% of the data is native viewing data, which no one is processing, so it's level 1 data. The intercal data we're pointing to the target instruments. Clario has hosted, and we didn't call it an open source science, but there was a science meeting in November, but basically invited a bunch of people scientists from the community with ideas on how to use and how to do their research with Clario data. So I'll end there. That's it. So we're supportive of what you're trying to do.
Thank you so much.
All right.
And we'll stay for the fishbowl. So next, our next speakers are Tom Newman and JP Swinsky from NASA's Goddard Space Flight Center. Tom is the project scientist for NASA's ISAT-2 mission, and JP is one of the system engineers on ISAT-2 working on cloud-optimized libraries. Welcome, Tom and JP. And I can see your...
Can I get a mic check?
Sound great, and I can see your slides.
Awesome, perfect. Thanks for that introduction. We do have these 2 pieces. I'll start by just introducing ISAT-2 briefly. We've been on orbit since September 15, 2018. Unlike some of the flagship missions, we just have a single instrument, and ours is called Atlas. Atlas generates 6 laser beams. It puts 6 footprints of laser light on the ground to measure the elevation of the Earth. As the name suggests, it's really optimized to measure changes in ice sheets, glaciers, sea ice, but it measures the heights of oceans, land, and clouds as well as it orbits. ISAT-2 as a project was recommended out of the 2007 Earth Science Decadal, and our design for our data processing system went through SRR in May of 2011, and then PDR and CDR in following years. So The system that we've built to meet those requirements is certainly not the cutting edge of today, but it was sufficient to meet the requirements as we got them those years ago. What we call the SIPS, the Science Investigator-Led Processing System, is our data system for ISAT-2, and it was based to a large extent on the SIPs developed for the original ISAT mission from 2003 to 2009. And that was done in order to reuse as much of the concept as well as some of the tools as we could for cost savings and complexity savings. So our ground system context diagram is here. The SIPs is in the red. Oops, let me go back by one. I clicked by accident. Red box over here, and that's the system that does generate the data products. We downlink data through the NEN over to EDOS and then into the SIPs, which lives at Goddard. It's that cluster of processing nodes that's in Building 32 at Goddard on a closed network that generates the products and then distributes them to our NSIDC DAC out in Boulder, Colorado for the world to use. We do have a few other dependencies here, but I'm not going to go through all of them in the interest of time. The major functions of the SIPs are here in the big yellow box in the middle. There's three main components to the SIPs. There's the facility, which is the hardware and switches and networks. There's the ASAS group, which takes the ATBDs from the Project Science Office and the science community and implements those in Fortran to be run in the SIPs environment. And then the third piece of the SIPs is the scheduling and data management system that automates the production of the data when the sufficient inputs are available for data to move through each of these processing steps. Our data product flow is here, a simplified version anyway. JP and I did some talking about the way the SIPs is currently set up, in that it's all on a closed network. None of it is open source, and what could be done. And the functions in the red box over there on the left are relatively low-level processing steps from level 0 up to level 1, and then to level 2, where we're calculating photon times a flight and turning engineering units into times, voltages, and temperatures. And all that culminates in our L2A product right here, this little ATL03. Those are our geolocated heights. This is the lowest level of information the science community is going to practically use. And they provide a latitude, a longitude, and a height at a particular time for each of the 6 spots for each one of the photons that the Atlas detectors detect. We occasionally reprocess from ATL02 to 03. Less often are we going all the way back to 00. That's that lowest level. Several of the steps from 00 to 01 to ATL01 to 02 are either ITAR sensitive or competition sensitive, in that we're using widgets or parts bought from industry, and then we're using their decommutation or knowledge about how their widget works in order to generate these geolocated photon heights. So that's all to say that it seems like there's a reason for something like a SIPs to exist that is closed to end users or to scientists. But all these other surface-specific data products over in the blue box on the right really can be open sourced. And currently, all of our products are run at the SIPs and the closed EBnet at Goddard, and then distributed by NSIDC. The science community can recode those things using the ATBDs. It's certainly a lot of work, but some people have done it. But we've been experimenting, and this is what JP is about to talk about, with a new way of generating surface-specific higher-level data products, where those results and products are driven by user needs. They're not subject to decisions I may have made, or the ATBD lead or data product lead may have made some years ago about length scales or aggregation length or how to best correct for A, B, C, or D, but really are up to the user. And that effort runs in AWS. It is called Slide Rule. The last thing I was going to say about this particular slide is that although the data flow arrows go one direction, by working with the Slide Rule project, we found a number of instances where, in generating a surface-specific higher-level product, it's actually informing how and what information content we're putting on this geolocated height product, or our ATL03s. So there can be feedback from these surface-specific products back into what we're doing in the geolocation of our data. And I think, JP, with that, I'm going to toss it over to you. Yeah, you want to take it from there?
Yeah, thanks, Tom. Can you go to the next slide? Yeah, so this is ISAT2 slide rule. It is an on-demand science data processing system that is funded by the ISAT2 program. And it's led out at the University of Washington, and it's a collaboration with Goddard. As Tom said, you know, some of the goals was really just to make it easier to work with the ISAT2 data. The photon cloud data, the raw data, is quite large and can be very difficult to work with. And also to target science communities that aren't targeted by the standard products that are currently available. So if you're in a community that doesn't have one of those higher level products for you, an on-demand service can meet their needs. But really, we did do this also with a view for the future and trying to model and demonstrate a new approach to distributing and generating science data. So next slide, Tom. Yeah, just click through one more. So historically, what we've been talking about, right? Institutions pre-generate their data sets. Those data sets get archived and made available via data centers. And then users come along, download parts of those data sets and perform their local processing. And that's the world we've lived in forever. Click one more time. And so what we're trying to demonstrate or model is a world in which institutions make science data available via web services. And then with those web services, data users integrate directly into them with their existing data analysis systems. And that's what we want to show you. So go to the next slide. There's a bit of a cartoon here, super oversimplification, but just to give you an idea of the vision that we have as far as what could have been done on ISAT-2 or future missions like ISAT. So you've got your satellite, sending the raw data down through the station, and then it's going to hit some on-prem processing system that's quite sophisticated, quite large, and that's going to run a pipeline. It's going to take you from the 0 to the 1, the 2, the 3, depending on your levels, maybe 4. And ultimately, all that data coming out of that pipeline is going to end up at an archive. And then I show on the right there, there's level 3 product downloads. And I did specifically say level 3 because in practice, with the size of some of the lower level products, in practice, you're really only working at the level 3 for the most part. So the vision that we have, if you click again, Tom, looks something like this. So, the raw data would come straight into a cloud data center. In that data center, there would be the regular on-prem processing, that blue box that that Tom drew, and they would produce the products right in the data center and make them available for in-data center access. And so if you're running in the data center, then you have direct access to those lower level products. Now, coming out of it, though, to users that choose not to run in the data center, we would provide customized level 3 product services. So it's not downloads, it's not files, it's services. So, a couple times this morning, people talked about the difficulty of managing files, downloading the files. ISAT-2, I think for the ATL03, the level 2 product is like 100 terabytes a year. I think there was another talk where they were saying it was 180 terabytes a year. Those can't be downloaded. And so in our system, there's no files. It's just a service. You request a product and it's returned to you in some binary form, streamed to you, and then we have a Python client that takes that binary form and presents it to the scripts, to the analysis system in native Python variables. Go to the next slide. I know I only have a minute or so left. This is what our system looks like at a very high level. We run in US West 2, AWS US West 2. We are taking advantage of the fact that NSIDC was one of the first groups to get the ISAT2 data into S3 in AWS. So that is the data that we access. We run all within the SMCE, the Scientist Managed Cloud Environment. That's a program out of Goddard for running in AWS commercially. We run on EC2s, and our user community in general is all running Python from Jupyter environments. Next slide. So just what can users do with a service, and just this change, right? When you're no longer thinking about downloading a specific data product and trying to manage something that's been pre-generated, what can you do? So I stole these from some scientists that we work with their permission. And this is some of the things that they've done. So, one thing is the Photon Cloud has different classifications. Right now, the algorithm that pre-generates the gridded surface elevation uses one classification, and that's what's been used. But we can allow scientists to explore different photon classifications and what that would do with the resulting elevation that would be calculated. And so you can say, well, what would the elevation look like if we used this classification system or that? Next one. This is one where two scientists were looking at a very rough iceberg, I believe, and the standard product was at a 40-meter resolution. And you can see the red dots are where an elevation is calculated, the blue is where the photons are. Well, they were able to work with the different parameters in the customizable product that SlideRule generates and find a sweet spot. And you can see, with a 10-meter resolution and using a certain classification algorithm, they were able to have a much more robust representation of the surface. When you're making a standard product, you kind of have to make decisions that suit everyone. And it's not going to work for all surfaces, but by exposing those customizations to the users, you can see a lot of gains. And then skip through this next one, Tom. I just want to go, my time's run out, so I'll just go here. So what can users do with the service? So this is another example. SlideRule is all backend. Our goal is to provide science data as a service. But when you do that, it can integrate and enable others doing front end and exciting work. So one of the scientists at University of Washington built a very simple widget-based front end in Jupyter, where using the leaflet maps, you're able to select some parameters, draw a bounding box, and immediately get a geodata frame. And now this is not what SlideRule is about, but this is what SlideRule is enabling. So by providing services that can integrate with other services, you can enable people to build some exciting real-time front ends. Okay, I think that is it. Actually, go to the last slide, Tom, with the last minute that we have.
Sure. Just tell me when to stop.
Oh yeah, just keep going.
Okay.
So we two more. Yeah, a couple more. Yeah.
Yeah. That one.
So we are open source and we are openly developed. And so for anyone interested, that's our website. We're under BSD, open license, permissive license, all the codes on GitHub and our documentation you can find there. So if anyone has any questions about it, I'd love to talk. Thanks.
Thank you, Tom. Thank you, JP. Great presentation. Always very informative. I know there's a lot of interesting questions on there, especially on SlideRule and how that can be used in the future as we build these new data processing systems. So if we move on to our next speaker, we have Brian Franz from NASA's Goddard Space Flight Center. Brian is the research scientist and assistant chief for science research in the Ocean Ecology Laboratory. He's also the Science Data Segment, SDS. So for those of you not familiar with the NASA vernacular, you'll hear a lot of SIPs, you'll hear a lot of SDSs, and we reuse a lot of these terms. So we'll have to make sure we have a glossary of these. But Brian is also the SDS manager for the PACE mission.
Can you hear me, Andy?
I sure can.
And can you see my screen? All right, yeah, so I'll be talking about the PACE Science Data Segment, or PACE Mission Data Processing System. I'm the manager of the PACE Science Data Segment. Sean Bailey and John Wilding are also online. Sean is basically my deputy in this context, and John Wilding is our data systems lead. So next slide, please. Yes, a bit of background about PACE. It will carry 3 instruments, the primary being OCI, which is hyperspectral radiometer, developed at Goddard. And then there are 2 multi-angle polarimeters contributed, one part 2 by UMBC, and SPEX-1, which is a contribution from the Dutch Space Agency. Our products include ocean color, or ocean biology and biogeochemistry, as well as aerosols, clouds, cloud optical properties, and polarimetry. And our customers, obviously, the earth science research and applications community, including ocean and atmospheres. And also, though it's not a baseline requirement for us, the instrument has obvious terrestrial applications as well. It's scheduled to launch in January of 2024 now. It is well into phase C. In fact, the satellite went vertical just this week. Next slide, please. All right, so some of the goals and objectives. The science data segment, PACE SDS, will produce the ocean color, aerosol, and cloud products from OCI, and polarimetry products from SPEX and HARP2. We also provide instrument activity scheduling and monitoring, and we provide support for calibration and validation requirements of the mission. Hit the slide again. So responsibility for the PACE Science Data Segment was directed to the Ocean Biology Processing Group here at Goddard. So most of what I'm going to talk about today is directly related to the OBPG. The OBPG is an integrated team of scientists and developers and operations staff that have been dedicated to end-to-end production of science data products from spaceborne sensors. We've been operational for over 25 years and a continuous evolution with an ever-growing portfolio of missions. The OBPG operates a multi-mission distributed processing system and a range of supporting facilities that are being augmented to support PACE. Next slide, please. All right, some of those systems include the OBPG data processing system, which I'll talk a bit about. Also, an integrated science software repository with a lot of code in it that we're able to reuse for multiple missions. We have an integrated validation system for matching up the satellite data to in situ measurements. Key to our infrastructure is that we're co-located with the Ocean Biology DAC, which is a DAC of record for PACE. The OB DAC also includes a sub-archive called CBAS, which holds all of the in situ data that we use for matching up and validation. It also distributes an application called CDAS, which I'll talk about a little bit at the end, but CDAS is basically a tool for data analysis and visualization, but also it serves as a way to distribute all of our science software as source code and provides a development environment for it. And I'll go into that in more detail in a bit. And also user support, of course, through an online forum. And we share the Ocean Color Web, which is a centralized portal for data and software distribution, documentation, and user support. Next slide, please. So this is a view of the PACE Science Data Segment architecture, which you see on the upper right. The dark gray box is the science data segment and the functional elements within it. On the left is our primary partners within the project, namely the ground segment and project science. And then in the green, you see our external elements. including the ocean biology DAC, which is external only in the sense that it's separately funded. But we also we have a science and applications team that provides algorithms and validation data. And the research community also provides validation data, and the vicarious calibration system, which is a NIST traceable source for calibrating specifically the ocean color measurements. So I'll just focus for a moment here on the data flow for science processing. We're pulling data from the ground segment, which is in this case, NEN is providing data for all the science data through an AWS cloud instance. We're also pulling the data from the MOC for the satellite data for principally the attitude and ephemeris information. So that data goes into our science data processing element and then gets processed up to higher level products. And then of course we have a reprocessing requirement to take that data and reprocess it periodically. And when we do that, we're basically just pulling the data back out of the DAC archives and refreshing it and putting new data back in. Next slide, please. Yeah, so just a little more detail. So the data ingest, we have several elements within the data processing. We do data ingest, of course, the acquisition, cataloging, archiving of the science data, and the housekeeping telemetry, as well as acquisition of ancillary data from various sources. We pre-process the data to level 0 and the level 0 and housekeeping data to time-based granules, what we call level 1A. Do the extraction and reformatting of ancillary data, and then of course the generation of higher level products from OCI and Specs 1 and HARP 2. And then, as I mentioned, the reprocessing requirements and delivery to the DAC. Next slide, please. All right, the ocean biology processing group's data processing system, we call that ODPS, utilizes a relational database management system, namely Sybase, and a lot of homegrown C code and script to schedule data acquisition, processing jobs, and file and device management tasks. The main piece of that is called the scheduler. This is very similar to what Robert Wolf showed earlier. But basically, each processing job is distributed to an available virtual processing unit on one of our clusters, Linux-based processing servers. The results are output and collected and cataloged and stored in one of our cluster of RAID storage nodes that are shared with the OBDAC. And of course, the ODPS manages the load on all the devices and the location of all the output products and the storage nodes. We have plenty of detail we can provide if there's interest in going deeper into the fundamentals of implementation and operation of ODPS. Next slide, please. So a little bit about the science software pipeline. I don't know if you're seeing this, but my slides are getting all screwed up.
Looks fine on our end.
Okay, great. So this just showing the science processing pipeline. This is for the OCI element. Fairly standard stuff. We take level 0 data and the spacecraft data up to level 1A, that then gets calibrated and geolocated to level 1B. And then that gets piped into our discipline specific level 1 to level 2 processing codes to produce the cloud, aerosol, and ocean color products. And that's basically the workhorse piece of this to go from level 1 radiometry to level 2 geophysical products. And then those can all be composited and into level 3, composited, binned, and mapped into level 3 products. So each of those blue boxes are the software components that we're developing. And again, the level 2 piece is probably the biggest part. That's where the data meets the science to convert into geophysical products. Next slide, please. So wherever possible, when we're developing a piece like this, we like to develop it in a multi-mission, multi-algorithm framework. And we've been doing this. Our bread and butter has been ocean color for many years. So this is showing the level 2 ocean color piece, where effectively we have a multitude of algorithms, both standard algorithms and alternative algorithms, and a lot of capabilities to vary the parameterization of those algorithms. And all we're doing when we add a new sensor is effectively updating the front end for how we read the data and adding lookup tables as necessary for the sensor specific aspects of the sensor spectral dependence. And effectively, we're building the same kind of framework for our aerosol and cloud requirements now. Next slide, please. And doing it in this way, it leads to a significant amount of software reuse. So this is just sort of a ballpark estimate of the amount of reuse I see for each of those components. But as much as 90, or in the case of level 3, 99% reuse, because those codes are effectively agnostic to the level 2 product that we're producing, as long as it's in a standardized format. Next slide, please. Similar pipeline for Specs 1 and HARP 2, just some minor differences because we have to co-register the multi-angle views. And also Specs 1 and HARP 2 are multi-angle polarimetry is fairly new to NASA, so the amount of reuse is not as high, as you'll see in next slide, please. Yeah, just essentially saying that the amount of reuse is not nearly as high because these are all new products and new algorithms, and a lot of it is much more experimental than the heritage operational ocean color aerosol and clouds from radiometry. Next slide. All right, so last slide, just some thoughts on open source. First and foremost, all of the OBPG science data processing codes are open source. This has been true since the 1990s when we started the CWIPS mission. We distribute the science software, including source code, and it's made freely available to the public through CDAS, as I mentioned. Fully supported with a build environment. It allows our community to reproduce any of these science products that we're producing, given the same level 0 or level 1 data. It also leads to what I think is probably one of the most highly educated communities out there, because the ocean color community in particular is very familiar, very knowledgeable about the algorithms and their implementation, and they operate in many cases more as partners than as end users, contributing algorithms, building their own algorithms, and using the codes that we provide to run alternate algorithms and alternate parameterizations. So another key element is that all of our OBPG data products are in a standardized format, and this obviously has makes life a lot simpler for our end users. Effectively, all of the data products are in a standard net CDF4. Everything that we control above level 1 or level 1 and above in standard net CDF4 that conforms to NASA Earth's data system metadata standards. I think a key here is that we control the data formats, regardless of where the algorithms come from or if others are contributing software. We will always modify it as necessary to conform to the standard data product formats. Lastly, about the ODPS itself, while it's not open source, it's technically speaking, it is highly leveraged, and it has been ported and shared with other facilities. First, of course, ODPS has provided the core science data processing for a multitude of missions within our organization, from CCCS, CWIFS, MODIS, VIRS, European missions like Maris and OLCI, the Aquarius mission, PACE, and now also Glimmer, which is a geostationary mission that we're also overseeing. And as I mentioned, ODPS was previously shared with GIS for the GLORY data processing system, and I believe it's still used there today, despite the ill-fated GLORY mission. And an earlier version of it, in fact, was provided as the basis for the emergency backup system that Robert mentioned earlier, that became ODAPS. And in fact, and it was ported to NOAA to support audio CTS back in the 90s. I think that's it for me.
All right, just on time. Appreciate that, Brian. Great talk. Our last speaker for this session is Oeg Kwan from NASA's JPL. Oeg is the JPL Science Data System Manager for the SWAT mission. And following Oeg's presentation, we will go into the fishbowl discussion for Q&A.
Thank you. Let me try to
Nice to
share
meet you.
my screen. Okay, let's see. Thank you, Karen. Yeah, my name is Oeg. I'm SWAT Science Data System Manager. In this package, I explain about the SWAT science data system from the perspective of open source science. Next page, please. The goal and objective in the three categories I summarized here. SWAT instrument, we have about 5 instruments. Primarily, it's a Ka-band SAR interferometer. It's a single pass interferometry, and every day it downloads about 7.9 terabits per day. Next page, please, Karen. Thank you. And out of about 1 terabytes of data that we are downlinking, about 97% of them is carrying SAR interferometer data. Based on those level 0 data coming into SDS, we produce 19 level 1 and level 2 standard data product, which is eventually the goal is producing hydrology and oceanographic data, sea surface height and water body elevation as well. The goal is to produce these products within 3 to 5 days after the sensor acquisition, data acquisition by the sensors. And routinely, we will deliver about 21 terabytes worth of data to DAC. And at the peak capacity, meaning SDS will deliver about 131 terabytes per day, particularly during the bulk reprocessing campaign. SWAT is one of the second-tier NASA decadal mission, and as such, in addition to that, SWAT JPL SDS team is SWAT project partnering with the CNES. So SDS perspective, our development and launch and operations support, those are all coordinated with the CNES. From the perspective of constraint on JPL side, at the peak capacity, we need to have about 2.5 thousand compute nodes at the peak capacity routinely, not routinely, during the bulk reprocessing campaign. Unfortunately, JPL, facility-wise, JPL do not have additional room to accommodate these additional compute infrastructure. Therefore, we had to go to cloud to support these bulk reprocessing campaigns. Because the data volume that we need to transfer between SDS and DACs are humongous, 131 terabytes per day at the peak capacity. So therefore, the constraint for us is really SDS and DAC to be co-located so that we can avoid the moving large data around while when the data, when the bandwidth of the network is limited. Next page. Overall architecture of SDS is probably very similar to others in the sense that SDS, on the left-hand side, SDS gets all the instrument data from the ground station. In case of SWAT, there is only CNES ground station that downlinks all the SWAT instrument data. Those data first goes to CNES Mission Center, which is at the second block in the left-hand side. CNES Mission Center is very similar to JPL SDS. However, CNES Mission Center has additional capabilities similar to JPL GDS capability, meaning that monitoring the housekeeping data and generating mission-related NCD data and providing it to SDS for the processing. In case of SWAP, all external auxiliary data are coming from external providers to CNES Mission Center only, so that we have a consistent data set across JPL and CNES. From JPL SDS perspective, we receive and ingest instrument data and auxiliary data. And we also receive standard data product generated by CNES. Then we deliver it to DAC so that it can be distributed to the end users. From data processing perspective, JPL SDS is responsible for level 0 and level 1 folder processing. But JPL is also responsible for bulk reprocessing, particularly that requires a high computing capacity. By the way, on CNES Mission Center, they are all processed in on-premise facility. So therefore, CNES team cannot support large-scale bulk reprocessing campaigns. So therefore, for JPL side, we had to go to in the cloud. So therefore, our system and the processing capability is highly scalable. From the perspective of the on-demand processing capability, the exact copy of the SDS system will be provided to ADT. It is at the lower right-hand side box, right below the JPL SDS. A copy of the SDS system will be provided to ADT, and then they will be used for on-demand processing for Project Calvel and ADT users. And also, we will set up at the request of ADT the product analysis environment where ADT can do processing and then can pull the data and then analyze the product. Next page, please. In the overall architecture, component-wise, primarily JPL SDS is all in Amazon Cloud US West 2 region, and the PODEC is co-located there. Within SDS, on the left-hand side is landing zone. It's primarily all data coming in. And then on the right-hand side within that box is the product store, whichever any data that SDS produces and any data that we need for processing and need for delivered to DAC, those are all stored in the Amazon S3 storage. In the middle, it is the key engine of our system. It's a processing control and data management system. It is primarily two types of clusters, or one PCM clusters, which responds for major data processing services, which is resource management and orchestration of jobs, cataloging data, and tracking the metrics. Then a PCM cluster is responsible for deploying compute instances to do the actual processing job. That's the bottom, within that dotted box, there's the bottom one. It says scalable PCM workers. Those are all Docker container-based technology that we are using, but our system is being being configured so that it can support different types of container technologies as well. And once we have a complete development done, as you see in the lower right corner, right below the SDS box, ADT on-demand processing capability will also be available in the cloud. Next page, please. As for the implementation technology-wise, the landing zone and the product store, those are primarily based on Amazon S3 storage. Therefore, we use several of Amazon services such as Lambda S3 event, including our homegrown scripts. For the product delivery, we use some common, I forgot the acronym. We use the Cumulus-based common messaging technology so that we can deliver product with the necessary metadata so that they can ingest without issue. For the PCM capability, we primarily inherit HiSDS system. It is an open source system used by NISAR and other missions at JPL. It relies on technical components like Elasticsearch, Redis, etc. And for us, for SWAT, we need to use Spot instances to support the bulk reprocessing campaign. Therefore, to us, in addition to all the technical components that HiSDS is using, the auto-scale Spot fleet management capability is very important for us. Next page, please. Oh, at the bottom, somehow the screen does not show correctly in the slide, but at the bottom, just to reiterate, ADT on-demand processing capability is primarily HDS deploying a copy of HDS system so that it can be used for ADT on-demand processing. Okay, next page, please. So some lines are kind of exceeding all the bottom, but I will kind of rely on my slide. Okay, so the reuse from the perspective of reusing legacy software, primarily the PCM core software is based on the open source HiSDS. That's the key component that we are leveraging for SWAT SDS system. And it is used by other component of integrated Earth mission systems in JPL. With NISAR, SMAP, OPERA, and MAP are based on the same the HiSDS that is open source. From the perspective of product generation software, we rely on legacy software from JPL and Connect. Those are radiometer processing, GPST, and radar altimeter. And there are some carrying processing software that we rely on legacy software. So therefore, for HiSDS or core PCM that we use, it is by nature is open source. But from the perspective of the product generation software, those are currently not in the open source yet. But obviously, we use many other open source third-party software as well. The international standard that we adopt, we use the OCG Open Geospatial Consortium web processing services that defines the standard about inputs and outputs for geospatial data interface. And we follow the time standard and the provenance information standard. From the product perspective, we use NetCDF and CF convention, and we conform to ISO metadata convention, metadata standard. From the perspective of developing in the open and collaborative environment, from the perspective of the PCM software, the key orchestration engine, it is developed, and all the code that we developed, when applicable, it is shared across multiple IMS SDS, meaning NISAR, SMAP, OPERA, and MAP SDSs. However, the development environment itself is not open to the public. From the science algorithm software perspective, we are currently these codes are developed in collaboration with the foreign partner, is CNES. And also, as such, we have several legacy and the proprietary software. So therefore, the development environment and software is not open sourced, or they are not developed in the open yet.
One more minute, Oeg.
Okay, from the perspective of cybersecurity, we are already in progress, and then I'll skip to the next page, considering time. Next page, please. Open source, I think the key message here is the project is embracing the spirit of open source science through the conformance of existing data and information preservation requirement. From the perspective of barrier, I think the schedule and workforce would be the concern in the sense that our launch will be November this year, and therefore changing anything at this point is really risky, but it might be a viable option at the launch. And also we have a proprietary data and algorithm software, so it may require consent from stakeholders for us to be able to develop open source science perspective. And what's really important to us is really requirement. So for us to kind of enable open source science support, additional open source science support, we need to have a clear requirement to be reflected in the SWOT project requirement. Next page, please. From the perspective of project pain point, SDS handling large data and at the scale of SWOT is really a big task. It has been always an issue to find a solid developers at the time that we need. And also because there hasn't been any similar type of software similar to SWOT. So finding out a large quantity of test data that can be suitable for flushing out the data system and to support the science sufficiently was not there from the beginning. So there is one of the key issues that we encountered. And then from the perspective of the processing system interface with the downstream analytics service, it's a primary HDS interface to the external world is S3 storage. So that's pretty much it. And then one last point is that it does not show in this slide. It's hidden. It's way outside the boundary. But it is that if you like, I'd like to share from my experience what might be helpful to the open source study is that from our experience reusing core PCM across multiple projects and the effort that we try to make it a standard, provide a standard solution and procedures, it has been very helpful across the project under IMS SDS. And I think it is a good indicator that the effort that this forum is trying to put together to make a common processing platform probably will yield a good, very tangible result. And also from mission with a large data volume like SWOT, for us to use multiple different cloud, the major blocking point was egress cost. So because of that, even if we would like to use multiple cloud vendors, currently we are kind of limited to using the Amazon cloud only. Okay, that's it for me.
Thank you, Oleg. Now we're going to switch over to the fishbowl discussion. Natasha or Elias, will you be leading the discussions on this?
Yeah, I think I'll be leading this. So just for the sake of time, I'm going to read different questions from our review, from our SAWG members. So actually this first question is from me, and it's for Robert. You said that oceans split from land. And my question is, how did that affect the number of deployments or shared resourcing for that data system?
Well, I think that happened back in the early 2000s. It made sense because the Ocean Color group at Goddard already had a lot of the capabilities in terms of sharing code and so on that Brian mentioned in his talk, and they had more experience and background in that area, and it just made sense. In terms of computing, I think the resources were pretty tight at the time, and I think maybe there was some more resources that kind of made their way into the system when that happened, and so it didn't really affect. It actually made it easier, I think, for us to concentrate on the level 1 land and atmosphere products at the time. So.
Okay, so I just want to
Long
make
time
sure.
ago, though. So.
Yeah, I just want to make sure that I understand. So the actual computing systems did sort of bifurcate, and did they like share back at any time, or create like kind of this community of, okay, we updated this code, you update your code, or did they kind of just break off as to 2 separate data systems at that point?
It was really 2 separate groups, I think, and again, there was the CWIS processing system at the time that there was a group of scientists who was working with that their processing group at the time, and instead of developing a whole new interface, I mean, I think it's all about the people. I mean, it really, if you think about how we work in doing science, our science data processing, it's about how we communicate with our science team and the community. And I think that was the real benefit of moving that ocean color work over. In terms of processing, I don't think it really made a whole lot of difference, except maybe the ocean color folks knew of ways to do some of the processing faster. I think there was some dramatic improvement in some of the processing that they were able to do.
Great.
We simplified it too.
Yeah.
By breaking it apart, it simplified it.
We simplified the suite of products that were being produced.
Yeah, I see.
Among other things.
And there was
I was going to add to what Robert said. I mean, it didn't affect the data system so much because they already existed. The ocean color data system just absorbed a new mission, and I think Robert got some extra capacity on his side.
Yeah. Things were less tight. I think at the time, if you look at the computer technology at the time, it was a challenge back then. Not so much now.
That's good to know. Thinking towards the future. This next question is for Chris. You mentioned that the system is moving to the cloud, and I think this is the perfect transition for that. You're moving to the cloud. What are the advantages and disadvantages that you as a project are seeing for that?
Oh, sorry. Okay, Chris Curry. All right, let me see you loud. Sorry.
Oh, so sorry. Yes, we're switching. I'm trying to mix it up between panelists. All my questions were stacked for Robert at first. I'm trying to popcorn a little bit.
Okay, so this is for the Clario system?
Yes.
Okay, yeah. So I think we want, it's just basically, we're a small project. We're trying to, for a number of years, we've been trying to get experience with the cloud, but we're just getting, that's our goal. Our goal and objective is to do all the science processing, the production and the analysis in the cloud. So I shared our plans on the development cluster. That's one implementation. And then our production system, I didn't get a lot of time to explain that, but we're learning the serverless technology, and that's a challenge. I've got a small staff, not a lot of experience, but that seems to be the way to go for data-driven systems that you let Amazon scale the resources and you don't have to build these dedicated clusters. So that's our goal. We still have some time to get there, but we do need to learn the AWS system and how to trigger Lambda and step functions. So it's cost savings to do, and I've been through this with Ceres. I've been through this with Calypso. The traditional way of doing science processing is to buy the biggest cluster that you can purchase. But with some of the things we're trying to do today, some of the processing requests that we have, and I shared one, was when actually doing simulation of our data, which we don't have. we don't have enough funds to buy a cluster large enough. And so for compute intensive, like simulation of data, that's an excellent use case for the cloud. So yeah, basically that's our goal, is to get to the cloud and do away with the clusters. And we're hoping, and I guess the other thing that I didn't get a lot of feedback was, I noticed that ESDIS, like 5 years ago, there was a push to get the data in the cloud onto S3. And I don't see that. I don't see that taking place. So, you know, that was one of our goals. You know, we're going to put our data in S3 and make it available to people. And I hope that others can do that too, because we're not going to pull the data out to do computation. We're going to do the analysis in the cloud. We're not going to download data to online servers, or excuse me, to on-site clusters. We're moving away from that, but the data's got to be in the cloud. So
I'll switch hats very quickly. This is Andy Mitchell. So as this is moving the EOSDIS holdings to the cloud, and we're doing a big effort actually this year to move a lot of data over 50 of our most popular data products. So we are actively doing that. So I'll take note that we need to do some more advertising on our plans there.
Yeah, thanks, Andy. And I was definitely going to say that we have that planned in one of the talks later in this session, or I think on day 3, where we have the docs presenting. So that's a great place to also get some more follow-up.
Yes.
And I think Thomas, you were going to jump in there.
Yeah, JP had touched on it, that ISAT2 was one of the early ones in that list, but yeah, there are others absolutely coming.
Great, thanks. I'm gonna jump back up for Robert. This one's for you. So you said that, you know, Modus Terra has been working in the open space for a long time, and that, you know, the code is publicly available. The question here is, how do you incorporate community contributions? So, you know, you can make the code available and people can submit pull requests and tickets and things like that. But how do you as a project decide when to allow contributions to that code base? And so how do you do it? And if you're not doing that, why not? And the main reason this came up is because it sounded like only the science team members could contribute.
Well, yes, that's a very good question. First of all, thanks. Yes, I mean, the arbitrators of the science code are the science team members. They're our trusted experts, and we rely on them to you know, do the development and you know, and provide the input. We don't have a ticketing system. We do have, you know, email communications. Of course, people can write us anytime and ask us to make changes or whatever. But it's really the science team members who are responsible for the algorithms, and we really feel that's very important that the science team members maintain that ownership of the algorithms. If you look at the way the algorithms were developed, there was a peer review process, and that process was an open process where the peers, before the algorithms could go into production, actually had to pass through a peer review process, and any new algorithms that are we're asked to run also have to go through that ATBD peer review kind of process. So that's a real good chance for community involvement. And plus, there are Rose's calls for new algorithms and we have a couple cases where we're running 2 different land surface temperature algorithms, 2 different surface reflectance algorithms in our system, and that I would consider, you know, contributions from the community, but through a more formal process than, you know, posting a branch on a Git repository.
Great, thank you so much. So I'm going to jump down. This one's for you, Chris. You mentioned transitioning to a serverless architecture on AWS. Do you see any risks or concerns with vendor lock by doing this kind of transition? any technology to fall back on if AWS serverless service doesn't work out in the long term, or if things were to change? Chris may have stepped away for a second. I'm actually gonna
No, I
redirect.
did step. I'm
Oh.
sorry. I stepped away. I missed the questions. I'm sorry.
Okay, no worries. So you mentioned actually in response to the last question that you're switching to a serverless architecture. And
that's our goal, right?
Right. And so the question here is, do you see any risks or concerns specifically related to vendor lock? Or, what if this technology didn't work? Like, what would be your fallback?
Well, the fallback is the current system that we have, the hybrid system. So we can modify that to support forward processing. So the serverless is nice when you have data that is uploaded to S3 and it generates triggers and kicks off these functions. So I think the technology is there to support what we need to do, because if you look at that slide I presented, the science processing, the science pipelines are still going to run in a Fargate server using Nextflow. And so they're still, so our long compute intensive applications. Yeah, that is a good point. The serverless, there's limitations with the AWS serverless architecture. Currently, I think the limitation is you can only run 15 minutes execution time. For a lot of jobs, that's not long enough. But what we're doing is we're trying to do some of the front end processing, the quick things in the serverless architecture, and then the long compute intensive jobs we'll still do using AWS batch, which is, we've had no trouble with that scalable architecture. I think it works very well. But the other thing is, if we had to go, if Amazon was a bust, well, the backup position is use the hybrid system, the current in-house system that allows us to run on our local cluster or run in the cloud. But we want to go completely to the cloud. So this will be, as far as I know, maybe one of the first projects. Our partners that are doing the level 1 LASP, they're using, their goals are to use the AWS serverless architecture to do the level 1 processing. But I know there are limitations and challenges. And so I would look forward to collaborating with other people within the ESDIS organization on that serverless architecture, because I think you for ingest, archive, and some other services, you're looking at that technology as well. So opportunities to collaborate.
Great, thanks so much. Oleg, this next one's for you. You mentioned that having the project level requirements are needed to drive open science and access. So is headquarters program offices ready to do this, or what hesitations have you had with needing this kind of guidance? Uh-oh, you're on mute. And I feel like I've just put you in the hot seat by the smile on your face. So apologies in advance.
No, that's okay. I think what I'm really referring to is that from SWAT SDS perspective, not at the mission level. SDS is level 4, so we are very deep inside a low level of the SWAT project. So really, kind of for everything to be, things to be developed in the open and the providing access to everyone, it requires some clear guidance about that SWAT SDS software shall be open source, for example. Then we need to coordinate with the partner and the other external source data institutions so that we can proceed to that route. But right now, what we do is, as I mentioned in the slide, at the end of the project, we make all the software available but archiving at the DAC. And all the data, however, that we produce is openly available as we produce them and delivering to the DAC. It's really about the software and the supporting ancillary auxiliary data. There are certain items that it really can need to, somebody need to drive for the project to do that.
Makes sense. Okay, so I'm going to popcorn back up to Robert here. Why did you choose to implement an object store instead of a regular network storage?
Well, first of all, we've been thinking about, bursting into the cloud and moving into the cloud over the years, and we want to make sure we're staying on the forefront of technology. And when I say the cloud, I mean the Earth Data Cloud, not some other cloud, because there are lots of clouds out there. We're using the object store because it improves our efficiency. We can talk directly to the object store instead of talking, going through our head nodes and various other things. I don't think there's really that much difference between a network store and an object store. The object store allows you to address individual objects and not have to go through the overhead that you might have to do if you're going through a network store. But I'm sure if there's that much difference in performance. Object stores also there's an open source tool we use, which is Ceph, which helps us manage the object store, and it gives us some capabilities there that we might not have if we were using a network store. But that's kind of a short answer.
Thank you. And we've got 3 minutes to go, so I've got one more question from the SAWG. And this one's back for you, Chris. When you used spot market compute, do you have any lessons learned on dealing with the spot market risks? For example, insufficient capacity of AWS Spot, which could prohibit Clario from meeting processing latency requirements or anything of that nature?
Yeah, that's a good question. So the forward processing, we don't need to run on spot. We could go on demand. The spot is valuable when you need to generate to run lots of code, and that's not our normal forward processing. Our normal forward processing, the intercalibration algorithm, is not compute intensive. It's very quick. We don't need to run on Amazon to do that. The rate of transfer simulations that we do are compute intensive. And so when I shared that we simulated a month of level 1 data in like 5 days of continuous processing. We're a small project, and I think that cost us like $6,000-7,000, to pay to Amazon. We don't need to do that on forward processing. Our requirements aren't that demanding. So spot is not a concern for us. But other missions that have to do a lot of processing, you should look into it, because you can save a lot of money. We saved, just for those runs, we would save 60% of the on-demand price. But you need a way to recover, because you will during the week. Other people are going to outbid you, and you're going to lose that EC2 node that you're running on. So it depends on the projects, how much money you're willing to pay to do your processing. With on-demand, yeah, there should be no risk of someone outbidding you and you losing that EC2 node. I hope that answered the question.
Yeah, thank you. I think that was, I'm going to put in the chat the Slido link again, and I'm just going to ask all the panelists to go ahead and take a look in there and see if you can answer or reply to any of those, since we are unfortunately out of time for verbal responses. And with that, I'm going to hand it back over. I think, Andy, are you running the agenda?
Yes, I just want to thank everyone who participated in this session. And then we will be taking a 10-minute break. And when we come back, we will be moving into our breakout sessions. So I'll see everyone back in 10 minutes. Thanks again to all the presenters. Very good session. Welcome back, everyone. I believe the next session will be the breakout session. So do we want to go into logistics? Patty or Karen or Sarah, how do we want to work logistics now?
So I think that the SOG had a few things to say about the breakout rooms, and then we'd like ESIP to just give us some instructions on how to get in.
Okay. Natasha, Elias.
Yeah, I can run through a couple of slides just to set up the scenarios that we want to achieve. So let me go ahead and share the screen. Hopefully you can see the screen now.
No, we can't, Elias.
Not. All right.
The share button should be in the bottom of the Zoom. There should be a big,
Yep.
There you go.
All right. I think you can see it now, right?
We're good.
Perfect. All right, so this is sort of the break room topics and some logistics of what we want to achieve here. So just a quick note here. The breakout sessions are really an opportunity for us to dive really deep into specific topics and to get feedback from you. So that the main goal is not to go into this breakout session and for the facilitators and leads to be the ones talking the most. We really want to pose some questions for you folks and really hear the community's thoughts. And so in that sense, we want to ensure that all the voices are heard and that we have a respectful communication here. So that is sort of some of the rules we should follow here. As a reminder, the study team here is responsible for recommending, the mission data processing systems architecture, and that's to meet some of these needs here. That's to make sure that we're meeting these ESO mission needs. We're enabling efficiencies. We're seeking opportunities for Earth system science, and we're promoting open science principles. So that's going to be the final goal of this study team, right? That we're looking at all these architectures and saying, well, here's the architecture that we recommend that meets these needs. The reason to kind of revisit this is that we want to make sure that the discussions we have in these breakout sessions are really helping to guide the study team towards fulfilling this goal here. And you'll see in a couple of slides what those breakout rooms are, and hopefully some of those will meet be more aligned with what you want to be a part of there. So each breakout session is going to be 30 minutes. There's going to be 6 rooms, each with a different topic. It's going to be led by facilitators from the study team. So the folks that will lead this are going to be the folks that do this study. So keep that in mind, that the feedback you're giving us is really helping to drive this study. The topics will all be the same each day. And since there's 6, you can, obviously you can join multiple, but I would encourage you to sort of stay within one topic per day because they're deep dives. If you kind of come in the middle, you may have missed certain pieces. But since we have these topics for the first 3 days of the workshop, you'll have multiple opportunities to either go to the same room, but you're also encouraged to go and visit different rooms and have your voice heard in that regard. So the next thing for you, you'll see the set of topics that we have and start thinking about which one you want to start off by joining today. You're very highly encouraged to participate into one of these rooms. So please don't take this like the time to go and take a break. I think this is that opportunity to dive deep and even explore some of these talks that we've had and get some of the questions that were maybe even posted on the Slido discussed within one of the rooms where appropriate for that topic. So please make sure you're participating. And then the last slide I'll show here is the 6 rooms that we have. And I'll tell you just quickly a little bit about that. And then we'll skip into how the rooms will be logistically, how you can access them and how you want to participate in those. So the first topic is sort of system development. And the goal is while that system is being developed, and again, mind you, this is the mission data processing system we're talking about here. During that time, what are the main approaches and challenges? And so things that we'll talk a little bit about are going to be how the teams are structured, reuse, open source, sort of the phasing, cybersecurity, cost, all these things can be discussed in the room. Again, though, these are not necessarily these are the things we have to discuss. These are just some thoughts and ideas, and we really want the rooms to be driven by you. The next room is system operations. So you can sort of see the theme here, right? You have developing the system, and now you're moving to how that system is operated. Again, what's the approaches and challenges within these? We'll look at architecture deployment, some ops, cons, roles, customers, cybersecurity challenges, sharing, cost models, especially cloud, and these kind of things become an issue here. Room number 3 is open source science. Those are, again, approaches and challenges, and really look at how do we start to think about these communities and this openness that we're heading towards for these architectures, right? What are the community contributions and code sharing? How does that look like? Accelerated analytics, improving participation from communities that may not always be represented. So a lot of topics within the open source science, obviously are going to be discussed there. Topic 4 is the data analysis needs. This you can sort of think of folks that may know the PGE term, right? This is building the science algorithm that essentially takes the data from the instruments and transforms them into scientific value. So those kind of topics will be discussed within this room, right? Anything in the algorithm development, ensuring the quality of the data that's produced, anything during the Cal-Val phases, and then supporting science and application use, which may be further within the project cycle there, and improving participation, again, from communities that don't necessarily have firsthand access to these things. Room number 5 is going to focus on open source software. So this is, you can sort of think open source science was number 3. Open source software is the software portion of that, right? What are the approaches and challenges? How do we incentivize more contributions? How do we, at the same time, uphold quality standards? What do you do with legacy systems, total cost of ownership, long-term support, anything in the realm of open source software. And last but not least is the mission data processing system architectures, right? We've seen a lot of the missions today. We saw missions, the ESO missions at our first workshop. What are those architectures? What do they look like now? And where are we headed into the future? Topics that are discussed there are going to be maybe standard-based interoperability, managed services, analysis platforms. What are the shortcomings today? What does the future look like? Anything within architectures. So hopefully that gives you a little bit of a view into the rooms, and what we're hoping to achieve from that room is really get your feedback and help us drive this study. So please start thinking a little bit about which room you want to dive into. And then I'll just turn it over to some of the rest of the team here who can tell us about how to actually do the logistics of getting into these rooms.
I'm happy to go through the instructions. So when I open up the rooms, everybody should see a message come across their screen, and you can go ahead and choose which room you want to be put in. If for some reason you don't see the message, just let me know, because I can manually place you in whichever room you'd like to go into. I did activate cameras and microphones, so you should be able to turn on your camera and unmute yourself, that way to have an active discussion inside the break room. Does anybody have any questions, or should I go ahead and just open up the rooms? All right.
I think we should dive right in.
Yeah, looks good. So you will get a message a minute before the room is going to close, saying that the room will be closing in 60 seconds. Okay, here we go.
So how do we, now we do the report outs of our breakout rooms. So don't know who wants to go first, or if we just go through the list that you originally spoke to, Elias. You and Natasha decide how you want to handle that. And Andy,
I think that's the right way to go.
Okay, Andy said his audio is not working. We've seen some other folks whose audio has also stopped working. Turn it over to you, Elias.
Again, for the next portion, we're going to do a report out from all the different break rooms. And I don't know if you guys noticed the feature, but you can actually look at how many people are in each of the break rooms and get a feel for that. So I would suggest let's just go down the list, and every team has somewhere about 5 minutes to go ahead and report out the highlights and the takeaways for this discussion. So let's start with the break room session 1. Go ahead, please.
This is Kurt. I can talk a little bit. We quickly moved from, this is the system development breakout, but we quickly moved into talking about development for the cloud and in the cloud, and separating resources. Amazon P cluster was a tool that people found useful, considered like Lambda functions to run processing versus allocation of EC2 clusters, and some variations on architectures and sharing resources that there's more details in the notes, but I'll leave it there for now.
Anything else to add, Kurt?
Adrian or Luke, do you want to add anything to that?
No, I'm okay.
Yeah, I think the only other comment I would share is, I think there was a good discussion about how to leverage shared resources. I mean, it was sort of thematically underlying a lot of the questions about, if you aggregate either multiple missions or enough jobs together, can you allocate those across a more consolidated system, whether it's EC2 or Lambda or on-premise supercompute, and then the understanding of how you would sort of track metrics on that usage or reapportion costs, even if it weren't direct costs, back out to the missions or the science needs of that community. So I think that sort of came through quite clearly.
All right, thank you folks for reporting out from room 1. So I'm going to go ahead and report out for room 2. We were the system operations approaches and challenges. And the main question that we tackled was, what are the challenges that are faced by the operations teams, and could the architecture have been done differently? Could the system have been architected differently to avoid those issues? And so we sort of dove in, and the main takeaways that we came out from that was access for external partners. So when you have an operating system, and obviously there's needs to interact with folks that are outside of the project, that was one of the main issues, and that was tough to do. In some cases, Thomas had mentioned that for ISAT2, they sort of moved some of the work over to LASP instead. That way they, LASP would be doing that portion. So there are ways to get around this, but there aren't necessarily good ways to try and keep it within the NASA, the organization's realm of things, and still provide external access to partners. So there seems to be a bit of a disconnect between the doing organizations and the folks that have to do the work with sort of cybersecurity, and then the folks that make these policies. So that was one of the highlights. Also diving a little bit deeper, things like software patching and security that had major impacts on cost and schedule, because they were very hard to try and plan for in the beginning. You sort of have a system and you're going to maintain, and you're going to do this, but you're asking for money every so often. You're not asking for money all the time. Maybe you have an annual or a multi-year budgeting cycle. So being able to plan properly for those had impacts on schedule and cost. And another word that we wound up talking about was unfunded mandates. Cybersecurity again seems to rear its head. That put a burden on teams, especially not knowing exactly what needs to get done, but things would come down the line, and you've got to do this and meet this mandate, or update your software to this level or this OS. And that puts burdens on teams to do that. And so the last thing we kind of talked about, and this is probably more of a general thing, is hiring the right folks with the right skill set is a high level issue, and it's no doubt it's also affecting operations. The other folks that were on this team for this discussion were Andy and Bernie. Feel free to add anything I may have missed there.
think you covered all the high points.
I agree. I think you covered,
All right.
you summarized it very well.
Okay, thanks. Let's move on to the third session. Go ahead, please.
The third session is the open source science approaches and challenges. So some of the key takeaways that we had was that currently there isn't really a criteria or process for community contributions for review of the algorithms and products, how to determine which products should be certified by NASA. And we also discussed that it's important to know, well, it's important where the products are hosted and where it's stored. Because where it's hosted and stored, whether or not the algorithms and the products can be trusted, and especially, how to identify which products and algorithms have gone through a vetting process. In addition to that, provenance tracking. There currently isn't a model for how data is stored and tracking which changes and revisions since inception. So that's something that should be looked at. And the last thing was open source contributor model for design of science teams to be able to truly enable community collaboration and participation using the highest value algorithms that's owned by the community to successfully change the culture around open science.
Thank you, Evelyn. Anything else to add from the rest of the folks from that breakout session?
This is Rama. I just want to add that it's not that we don't have a way of tracking changes. We do track version numbers and we record the changes that happen from version to version. The question we were raising was mainly how would you extend that to the broader community contributed products? I think that's the issue more so than the standard products that we're currently doing.
Thanks, Rama. Thanks for the clarification.
Yeah, if there's no further comments from that one. Let's move on to session 4, which is the data analysis needs.
Hi, can you hear me okay?
Yep.
Okay, great. So we talked about the science data analysis needs. And then we have a relatively smaller breakout session. And then we have a couple of key takeaway points from this discussion. So the feedbacks we heard is that there is a trade-off between the products, the mission support products and the analysis ready data product generation, especially with the cost cap that is currently in place. And also we noticed the importance and the trend to make the analysis ready data products. And then this ARD should be a level 1 requirements. And it is extremely important to show how such products are produced, and the reproducibility here is very important. And we all recognize the importance to leverage the shared resources and the reusability of the tools and the different components of the tools. So there is an urgent need to converge on the reusable components when designing MDPS for multiple missions. And we also noticed the general lacking of the feedback loops between the relatively closed product development environment for lower level products and the relatively more open environments for higher level product generation. So such engagements, the feedback loop and the engagement between the science team and a broader science community should happen early on in the mission. So early engagement is very important. And the process for contributing code to support open source science should be more agile. And for example, the releasing of the legacy code bases should be made more efficient and faster in the process, which means the management approach might need modifications, need new changes. And there is another challenge identified, which is the different centers running multiple missions have really separate software bases. So this again tells us the importance of to have a reusable components and the shared resources. And there is also the need to continuously improving the products, improving the software after the commissioning of the mission. This is also very important to satisfy the data analysis needs. So Wenying, Andy, if I miss anything, please feel free to.
So there's another aspect that discussed during today's breakout session is the workflow management, how that can help the the team to progress, and also the importance of developing those workflow softwares with the reusability in mind. So that's all I have to add. Thank you.
Thank you, folks, for that thorough feedback. Sounds like you guys had a lot of interesting discussions within that breakout session. Let's move on to session 5, which was the open source software.
Yeah, so we had the open source software approaches and challenges. We were discussing, incentivizing open source communities, contributions, intellectual property, securities, and trust. And some of the key takeaways were really, stop trying to build new things. There's a lot of opportunity for NASA to add new life into existing efforts, and help communities move forward. How do we turn these communities into stakeholders? Headquarters needs to provide guidance and support. It seems like there's a lack of clear guidance top down as far as policies go to reach this open source science and using via open source goals. Many of the policies seem directly oppositional or adversarial in terms of how you incorporate open source software, provide open source software, collaborate on open source software. There seems to be like a lack of documentation and buy-in that can be communicated to developers and project managers and things like that for various projects. There's this culture and communication issue in terms of, making open source projects discoverable and discovering new projects, a little bit of a marketing misalignment we heard for some of the stuff that NASA is doing that people don't necessarily know about, where you could get more buy-in and potentially more contributors. How do we was it yeah, so that's roughly kind of it. If there's anything I missed, I'll let any of the participants chime in. Dan,
yeah, I think
Alexi.
I was going to say, I think you did a pretty good job. There was an interesting discussion just at the end too about like how seriously, we need to take security concerns. Are those overstated as a barrier that's limiting progress? And I don't know if we solved that, but that was another very interesting thread.
Yeah, nothing for me. I thought you did great.
Okay.
Thank you.
Yeah, also on the security item, maybe I just again, it seems like there's lack of clear policy guidance and for developers and users on that, and really rationale with some of the security rules. Some of the policies seem very outdated, so and they need revision. At least the group thought so. Sorry. Yep. Thanks for reminding me, Leslie.
Oh, thank you. Great job.
definitely on the topic of security, that seems to be a theme that we're hearing from a lot of the breakout sessions, right? Sort of the need for security, but yet the need for openness and access and being able to do the job that we're tasked to do. One thing you did say earlier caught my attention a little bit more, though, Andy, was you were sort of saying that there could be more direction for the headquarters level or the management level and to how to do some of these things, and specifically in your guys' case in the open source software. So I would say maybe that's another topic to try and explore even further, and maybe if you can come up with some details that can go back the other way in terms of then helping to shape the architecture here that we're trying to come up with would be helpful. All right, I know we were scheduled to end at 2:10, but we may run a few minutes over. So let's go to MDPS architectures, breakout room 6.
Can you hear me? This is Luke speaking.
Yep.
Okay. So we actually had a very, very good discussion in the architectures breakout session. An overall theme that was brought up by several people was that recommendation to the working group is to kind of identify what are the common denominators, the fundamental services, so to speak, that are going to be relevant for the architecture. I think that was more like the overall theme, rather than going down, different areas of different advanced capabilities. We need to start off first with what are the common essential services effectively. And I think there's also a great point that Doug had brought up as well with respect to effectively recognizing that there exists multi-cloud equivalents of services, meaning that across the different cloud vendors, there are equivalent similar services being provided. And because of that, I think the point was made that the vendor lock-in that many have brought up may not be as high of a risk as we may originally think. Right? It kind of depends on who we talk to. Another follow-on to that was the interoperability and the design from that. Regardless of whatever the cloud provider or approach or architecture, the interoperability and across the different areas, whether it's interoperability of services or APIs or even containers. Bob mentioned about algorithm packaging into containers is one of the other important areas as well. We also had another interesting discussion about fork and lift. That term has been used before, but effectively, I think it boiled down to that, fork and lift approaches to the cloud do not seem to be working as well. We really need to embrace more and more cloud native approaches, whether it's serverless or managed services or the like, but that was an overall theme. And I think there was also an interesting comment discussed as well with respect to that. On one end, leveraging all cloud native is great, but it was also pointed out that we also need to acknowledge that there are a lot of still useful and reusable tools that are not AWS centric, right? AWS is just one vendor. So how do we balance that? And I think one example that was brought up was Terraform versus CloudFormation. Finally, we ran out of time, but we were just about to discuss about recognizing overlaps in the scope of the architectures of the MDPS, which focuses on the before the archive scope, versus some of the analysis stuff that we heard earlier this morning with respect to that scope that's more focused on after the archive. So it's just one point that there's certainly overlaps in the architectures of these two. I think that was mainly it for today.
Thank you for that, Hook. Hopefully folks found the breakout sessions useful and they were able to dive deep in there. We'll continue to have them in subsequent days. So feel free to jump across or continue in the same rooms as you've been. But that's the report out from the sessions. Anything else to add from the organizers before we end for today? Turn it over to Andy Mitchell, Andy Bingham.
Great job. A very long day, but I think it was an excellent first day to the workshop. I look forward to our continued discussions tomorrow with our first session kicking off at the same time. And if you have any questions in the meantime, feel free to email myself, Andy Bingham, or anyone else on the team. And again, if you want to forward the message on the Zoom link, please do not, but have your colleagues register. And I'll see everyone tomorrow. Anything else, Andy, or anyone else on the steering committee?
I think some folks are staying on to check in with the ESIP folks.
Yes. So all attendees are allowed to leave. Thanks, everyone. Thanks for the participation.